If the universe did not begin with a big bang and will not end with a final destruction, then is everything caught in an endless loop? The question lands like a stone thrown into a dark well. It sends concentric ripples through imagination, through the scaffolding of certainty that has held together cosmology for a century. It is at once simple and devastating. A single rearrangement of an assumption and the story of existence reorders itself. For a moment, the comfortable beginning and inevitable end. Two neat bookends seem optional, like chapters someone removed and hid. In their place is the uncanny possibility that time itself has a memory, that the cosmos breathes in and out, that history folds back upon history. The feeling it evokes is not pure terror nor relief, but an odd vertigo, the sense of being a brief, bright thought within a mind that has been thinking for a very long time. This opening idea does more than provoke. It reframes every question about origin, cause, purpose, and fragility. If beginnings are not absolute, then origins become echoes. If endings are not final, then extinction might be temporary. Civilizations might be footprints that vanish and reappear under shifting sands. Human perspective, so accustomed to linear narratives, to cause then consequence, suddenly looks provincial. The Earth, with its layered sediments and fossil diaries, feels like a palimpsest of one page among many. The shock of this question is both intellectual and existential. It forces an evaluation of scale and of the humility due to any species that presumes to be the final or first witness of cosmic events. The idea that the cosmos might be cyclic has its own aesthetic, repetition, rhythm, a cosmic metronome. It is an aesthetic that invites metaphors, breath, heartbeat, returning seasons, but it also invites practical interrogation. If the universe repeats, in what sense is it the same? Are the cycles identical, or do they vary like weather? Do they leave traces, like fossils in a rock layer, that reveal what came before? The human mind craves evidence, and the modern narrative of cosmic origins centered on the Big Bang offers a framework rich with measurable signatures. To challenge or expand that framework is to ask where those signatures came from, and whether they might themselves be residues of something deeper. The Big Bang, as a concept, is both precise and popular. In scientific parlance, it is the name for a set of observational consequences, the universe expanding, the existence of a cosmic microwave background that is the faded glow of an earlier hot, dense state, and the predictable abundances of hydrogen, helium, and trace light elements. But in the public imagination, Big Bang often becomes shorthand for the moment everything began, a cosmic birth so singular and absolute that before it nothing existed. That interpretation is powerful and poetic, and it is the version that most people carry in their mental pocket like a talisman of origin. Yet when the narrative is allowed to breathe and the jargon to loosen its grip, the Big Bang becomes less a single, definitive event and more a description of a phase, a hot, dense phase in which matter, radiation, and space-time behaved in ways extremes can demand. There is a sequence, and some of its milestones read like chapters of a slow-motion crescendo. First came expansion. Redshift, the steady stretching of light from distant galaxies, was observed as a giant-scale recession. Spectral lines, the fingerprints of atoms, were found shifted towards longer wavelengths, the farther away a galaxy was. This was not the whisper of local motion, but the measurable hand of space itself expanding. The discovery transformed the sky from static tapestry into a dynamic history. Galaxies as distant beacons whose light arrived delayed in time, revealing past states of the cosmos. The implication was immediate and unsettling. If galaxies recede now, then running the equations backwards implied a compact, hotter past, an earlier epoch when matter and radiation were far closer together. Then came the relic glow, the cosmic microwave background, an almost uniform field of microwave photons bathing the sky, discovered serendipitously as a faint hiss by instruments tuned for other purposes. It was a fossil of the universe's youth, a cooled ember of a once brighter fire, carrying with it a thermal spectrum and minute temperature variations that encoded the seeds of structure. The existence of this background radiation was a striking confirmation. If the universe were once dense, then the radiation from that epoch should be visible today, red-shifted into microwaves. Its discovery was like finding aged parchment with a fiery watermark, the imprint of a hot, early state preserved in the present. Closely allied is the abundance of light elements. The relative amounts of hydrogen and helium in the cosmos and the presence of traces of deuterium and lithium are not random. They follow predictions from nuclear physics applied to an expanding, cooling plasma. The first few minutes after the hot phase permitted nuclear reactions that forged helium from protons and neutrons in predictable ratios. That the cosmic inventory matches these calculations is a persuasive line of evidence. The cosmos was once a crucible, and the isotopic fingerprints are the record left behind. These pillars, expansion, background radiation, elemental abundances are the scaffolding that elevated the Big Bang from a speculative model to a robust scientific paradigm. They anchor mathematics to observation, turning hypothesized epochs into testable predictions. Yet even this robust structure contains seams and questions, places where the story is incomplete or where anomalies chafe against tidy narratives. One seam appears at very early times, where the known laws of physics, quantum mechanics, and general relativity strain against each other. The logical extrapolation to earlier and earlier times leads to conditions where densities and curvatures grow without bound, a singularity in the equations rather than a comprehensible physical state. Many interpret this as a signal that the current mathematical language is being pushed beyond its domain of usefulness. The singularity is a mathematical artifact, not an epoch that can be probed with instruments. The troubling singularity prompts two responses: improve the mathematics, seeking a quantum theory of gravity, or reconsider the cosmological narrative, perhaps the present. Expansion was preceded by something else. Another seam is inflation. This is a chapter added to the standard story to solve several conceptual problems: why the universe is so homogeneous on large scales, why it appears flat in its spatial geometry, and how tiny quantum scale fluctuations were magnified into the seeds of galaxies. Inflation posits a brief period of superluminal expansion, space itself ballooning faster than the speed at which light could cross it. The mechanism, while powerful in explanatory scope, is speculative in some details. It relies on fields and potentials that are not yet directly observed. In the vocabulary of philosophy, inflation is an inference that fills a lacuna, and in the vocabulary of science, it is an elegant hypothesis that demands ever finer tests. When the narrative is followed forward from the hot phase, a chronology emerges from a plasma of protons, neutrons, electrons, and photons to a cooling universe where nuclei formed in minutes, where atoms formed in a few 100,000 years as electrons combined with nuclei and released photons to drift freely. Those photons are the cosmic microwave background. Hundreds of millions of years later, the first stars ignited and structured galaxies clusters. Filaments grew through the influence of gravity and the scaffolding of dark matter. The long arc from simple particles to complex chemistry and ultimately planets and life plays out over billions of years, an unfolding saga of structure emerging from nearly featureless beginnings. And yet, the Big Bang narrative, as compelling as it is, does not answer the most wrenching question posed at the outset. Is this whole sequence a single, unique act, or is it one cycle in a recurrent drama? The scientific account is often agnostic, focusing on modeling what can be measured, but the philosophical and speculative impulse presses on. Psychic models are being proposed with varying emphases. Some imagine a cosmic bounce, where a prior contracting phase reaches extreme density, then rebounds into the expansion observed today. Others conceive of a conformal cyclicity, where the infinitely expanded, heat-death-like state of one eon transforms conformally into conditions appropriate for another eon. Still others suggest ekpyrotic collisions, brain-world scenarios where higher dimensional surfaces collide and reset the cosmology. These alternatives are not fantasy in the pejorative sense. They are temptations, attempts to place the Big Bang inside a longer, perhaps infinite, narrative. Each carries its own set of predictions and difficulties. A bouncing model must contend with how entropy behaves across cycles and whether the bounce erases or preserves information. A conformal cyclic model must explain how the universe transitions between scales and why certain imprints might survive the passage. In all cases, the central scientific demand remains: if cycles occurred, what empirical traces would they leave? The quest becomes a search for fossils not of creatures but of cosmologies, subtle anomalies in the cosmic microwave background, unexplained statistical features or distributions of primordial elements that refuse to fit the single bang template. The emotional tenor of this inquiry is ambivalently grand. For humanity, contemplating cycles is at once undermining and consoling. On the one hand, the possibility that geology, biology, and even civilizations might be but temporary notes in an old symphony diminishes anthropocentric hubris. It suggests that the memory of a species could be erased by cosmic bookkeeping. On the other hand, cycles offer a kind of continuity that linear narratives cannot. There is resilience in recurrence, the sense that reality persists through variant instantiations. The Earth, with its deep time of rocks and ice and life, becomes a paltry microcosm of the grand cycles that may govern the cosmos. There is also a practical dimension to the shock question. If the universe recycles, the implications for the preservation of information and the survivability of intelligence change. For human curiosity, this is not merely metaphysical musing. It translates into concrete research agendas, searching for anomalous isotopic ratios, developing instruments to detect faint non-Gaussian patterns in the cosmic microwave background, re-examining geological layers for signatures that could plausibly be non-terrestrial in origin, and testing the limits of gravity at extreme densities. The quest for traces of prior eons is, in essence, an expansion of archaeology to a cosmological scale, the excavation of time itself. But until such traces are found, the Big Bang remains the most parsimonious description of observable reality. The universe expands, a relic glow pervades space, and the elemental makeup of the cosmos follows the script nuclear reactions prescribe. These are facts anchored in data. They create a narrative that is scientifically robust and aesthetically compelling. They also allow the mind to wander, permitted by the very success of the model to ask, where did the initial conditions come from? And could they themselves be derivative? In the quiet between questions and answers, the human perspective feels both minute and privileged. Minute, because the timescales involved are so vast that every political life, every city, every species lasts only a breath. Privileged, because, in the brief interval that humans have walked the earth, they have developed the capacity to ask such questions, to build instruments that can detect the faint afterglow of a universe billions of years old, and to translate spectral lines into narratives about primordial nucleosynthesis. That juxtaposition is the source of a particular kind of awe, the recognition that small observers can, through reason and measurement, access histories far older than their own species. The question that opened this segment, whether the universe could be trapped in an endless loop, has not been answered here. Rather, it has been reframed. The Big Bang, with all its evidentiary support, is described not as the definitive beginning for absolute reality, but as a milestone in the chronology that scientists reconstruct from observation. It is the bright page whose edges are crisp because of the fossilized radiation and isotope ratios it left behind. Beyond those edges lie speculative territories, mathematical singularities that may signal missing physics, inflationary proposals that expand the explanatory palette, and psychic models that attempt to embed the hot phase within a longer narrative. And there is a human afterthought threaded through all of this, whether the cosmos repeats or not. The impulse to look backward and to imagine what might have preceded is an expression of the same curiosity that has driven exploration across millennia. It is the habit of the mind to seek continuity, patterns, and origin stories. Sometimes those habits lead to clear answers. Sometimes they reveal deeper mysteries. Either way, they reshape humanity's understanding of place and time. As the segment closes, the paradox remains both a challenge and a lure. The Big Bang provides the most precise map available, but the map's borders are porous. The listener is left with a sense of suspended inquiry, the immediate facts of expansion, background radiation, and primordial nucleosynthesis stand firm. Yet the larger question, are these the first notes of a lifelong symphony, or merely the opening measure of a repeating? Movement remains an invitation. It is an invitation to look harder, to build sharper instruments, and to listen for faint echoes that might betray a memory older than the light itself. The next chapters of this exploration will move from the cosmic to the terrestrial, from the hot bath of the early universe to the layered archive of Earth, and eventually to the unsettling possibility that the planet's deep time might hold even stranger secrets, traces not merely of geological epochs, but of forgotten intelligences erased by the slow, indifferent processes of time. 3. V. Could the cosmos have been born like a phoenix, rising not from nothing but from the ashes of a previous existence? That question sits at the center of this chapter like a single, impossible melody that insists on repeating itself. It is an image that produces an immediate emotional tug, a mixture of vertigo and consolation, and it frames the exploration that follows. The Big Bang, so often rehearsed as the ultimate origin, might instead be a punctuation mark in a far longer sentence. To think otherwise is to accept an unsettling humility that what is most immediate to human eyes, the warming glow of distant microwaves, the steady recession of galaxies, the chemical ledger written by nucleosynthesis, could be the echo of an older music. The observational pillars that made the Big Bang more than a philosophical claim still stand, and they deserve to be repeated with a reverence reserved for empirical truths. Space is expanding. The redshift of spectral lines maps the recession of distant galaxies into a measured cadence of increasing separation. The cosmic microwave background is a fossil glow, almost featureless, but studded with minute anisotropies that encode the seeds of structure. The abundances of helium, deuterium, and lithium speak in the careful language of nuclear physics, matching what a hot, dense early epoch would have produced. These are not metaphors, they are signatures that anchor theory to measurable reality. Yet signatures can also be legible in multiple ways. The same fossil could be an impression from a single event or a worn print left again and again by a recurring pattern of motion. There is a subtle distinction between saying that the Big Bang is an empirically robust description of the earliest accessible phase and saying that it is the unique, singular birth of everything. The former is defensible, the latter is a metaphysical leap. The mathematics of general relativity, when chased backwards in time, leads to a point where curvature and density diverge, a singularity. But physicists treat singularities as red flags, an indication that the current mathematical framework has been stretched beyond what it can reliably describe. When the map tears, it asks for new cartography. Quantum gravity, a theory not yet in hand, promises to smooth the tear. If that smoothing occurs, then the story need not terminate at a single originary instant. Instead, the pre-Big Bang landscape might be reconstructed as a different phase of the cosmos, contraction before expansion, different laws in different epochs, or conformal metamorphosis from one eon to the next. Different models propose different mechanisms for that smoothing, and each carries its own emotional texture. Bouncing cosmologies imagine the universe contracting, compressing into a dense state, then rebounding into expansion. The image is physically dramatic, space-time collapsing like a slowly sucked-in diaphragm and then snapping outward. Ekpyrotic scenarios draw on higher dimensional geometry, picturing a collision between branes, extended objects, in a larger dimensional bulk, each collision igniting a new hot phase that appears from inside like a beginning. Sir Roger Penrose's conformal cyclic cosmology is more austere. It suggests that an infinitely expanded, entropic universe can be mathematically reinterpreted through a rescaling of space-time into conditions indistinguishable from a new Big Bang. Each possibility reframes the familiar facts, not by denying them, but by embedding them in broader cycles. What any cyclic picture must confront is entropy, the arrow of time. Thermodynamics, in its blunt empirical language, insists that entropy increases. Disorder, once grown, rarely shrinks. If the universe repeats, how does the bookkeeping of entropy reconcile across epochs? Does each cycle reset entropy, and if so, by what mechanism? Or does entropy accumulate, making successive cycles longer, smoother, or altogether qualitatively different? These are not merely mathematical curiosities. They bear on the emotional resonance of recurrence. A cosmos that repeats identically would be mathematically comforting, but physically improbable in the face of entropy. A cosmos that repeats with variation, carrying scars and differences from one cycle to the next, offers a richer, stranger story. Continuity without exact repetition, memory without permanence. Memory is the other hinge of the debate. If the universe cycles, does it leave traces that survive the reset? Scientists have turned the question into an archaeological hunt, but at a cosmic scale. Rather than sifting through soil and pottery, they examine the cosmic microwave background for anomalous imprints, subtle rings, non-Gaussian patterns, or atypical alignments of temperature fluctuations that might betray pre-Big Bang influences. Gravitational waves, ripples in space-time produced by violent events, have become another promising ledger. A particular spectrum of primordial gravitational waves could be a fossil of a bounce or a collision, an imprint from before the hot phase that could survive into the observables of today. Even the distribution of primordial black holes, if they exist in certain abundances, could hint at seeds planted before the hot era. These searches are delicate and obsessive. They are the work of meticulous observers trained to trust anomalies while doubting illusions. The emotional texture of this search is acute. There is the thrill of possibility, the thought that, by listening carefully to the sky, one might hear a whisper from an age not just older than humanity, but older than the conventional cosmological narrative. There is also the anxiety that the universe might be fundamentally inscrutable in this regard. Instruments have limits, noise exists, data must be interpreted. An apparent signal can be a statistical fluke or a miscalibrated sensor. The human mind, capable of poetic leaps, is also prone to pattern seeking. Scientists counter this tendency with rigor, cross-checks, independent measurements, simulations. The tension between imaginative speculation and methodological restraint is itself part of the drama. Beyond the technical, the speculative cosmology carries philosophical weight. If cycles occur, the idea of a first cause, cherished by some intuitive narratives, dissolves into a chain without beginning. For some, this is liberating. Origin myths were never meant to be scientific accounts, and their replacement by a more expansive narrative need not diminish wonder. For others, the loss of a unique starting point feels disorienting, a removal of the cosmological anchor for meaning. Either reaction reveals how tightly the concept of beginnings is bound to human emotional architecture. People are creatures of narratives, beginnings, middles, and ends. Cyclic cosmology challenges that narrative instinct, proposing instead a tapestry without a single edge. There is another, more anthropically unsettling consequence. If the cosmos has cycled many times, then the possibility of past civilizations, not merely planetary lifetimes, seems to acquire a different hue. The Earth is a geologic palimpsest, and so is the sky. Geological strata are, by their nature, incomplete. Plate tectonics recycles crust, erosion wipes clean, continental collisions bury and obliterate. The farther back in time one looks, the sparser the archaeological record becomes, until the record is drowned in uncertainty. If cycles reset global conditions at extreme scales, high-energy events that erode planetary surfaces or strip atmospheres, then the chances of preserving a technosignature across eons are vanishingly small. A civilization sophisticated enough to alter planetary geology might nevertheless be as ephemeral as a footstep on a beach washed, away by tides stronger than it could conceive. That prospect is not merely melancholic, it refocuses the scientific approach. Instead of expecting obvious artifacts, monolithic structures, or preserved devices, the hunt for ancient intelligences across cycles would center on subtle anomalies, isotopic ratios inconsistent with natural processes, mineralogical assemblages that betray technological metallurgy, anomalous concentrations of transuranic isotopes, or deviations in planetary atmospheric chemistry that cannot be explained by known geophysical processes. On the cosmic scale, similar thinking applies. Look for fingerprints in background radiation, or in the distribution of galaxies, or in fundamental constants that might have been nudged by earlier epochs. The search becomes cautious, patient, and multidisciplinary. At the heart of this caution is an epistemic humility. Deep time erodes certainty. Human timescales are narrow ribbons within a vast canvas of eons. The act of reconstructing past states is always inferential, a process of making the most faithful story that fits available evidence. Paleontologists reconstruct ancient environments from fragmentary bones. Geologists read climates from isotope compositions. Cosmologists decode early universe physics from photons that have traveled for nearly the age of the universe. In each case, the narrative emerges not as a single definitive truth, but as an ever-revisable model, subject to new data, new methods, new theoretical insights. It is worth dwelling on the image of Earth as a palimpsest. Layers of rock, like overwritten pages, contain traces of biospheres gone by, but the act of overwriting is relentless. Oceans rise and fall, glaciers scour and deposit, sediments compress into stone and later uplift, exposes them only to be eroded again. Even the most durable of traces, isotope shifts locked into zircon crystals, anomalous deposits of rare elements, must be interpreted within messy geological stories. The possibility that an entire prehistory could be smoothed out by planetary processes is sobering. It suggests that even if the cosmos hands down echoes of past aeons, the planetary record might be sparser than one would wish. Yet there is a counterintuitive consolation in that sparsity. Humanity's knowledge and curiosity are products of fragility. The mere ability to pose questions about cosmic cycles and to design experiments sensitive enough to detect subtle signatures is itself remarkable. The history of science is a story of cumulative refinement, of instruments coaxing whispers from the void into comprehensible notes. That capacity may be transient in cosmic terms, but while it exists, it opens vistas into scales and epochs unimaginable to previous generations. Whether the universe is a single unfurling or an eternal metronome of breaths, the act of looking, measuring, and interpreting is a testimony to a particular window in cosmic history when complexity had evolved enough to reflect on its origins. Practical consequences of cyclical cosmologies have begun to shape observables and research priorities. Cosmologists design experiments to map the microwave sky with greater fidelity, searching for fingerprints that would be inconsistent with a single hot phase. Detectors sensitive to primordial gravitational waves are now a frontier, a particular polarization pattern in the cosmic. Microwave background would be a smoking gun for inflationary dynamics or for violent events before the hot era. Laboratory physicists push the boundaries of the standard model and of quantum gravity proposals, because the nature of a bounce or a conformal transition depends intimately on high-energy physics. Geoscientists revisit layers once dismissed as uninteresting, seeking isotopic oddities that might signal processes beyond simple geology. Across disciplines, the work is incremental, anchored in method, but animated by that larger, almost mythic question about recurrence. The psychological effect of this work is complex. For some, the idea of cycles reintroduces a cosmological narrative that echoes ancient cycles, seasons, tides, the births and deaths woven into myths. For others, it is an intellectual challenge to devise ways of separating noise from signal on scales where evidentiary returns are slim. Both impulses feed the same enterprise, the desire to test whether the universe has a memory. That desire is both scientific and human. It is science because it demands falsifiable predictions and empirical verification. It is human because it seeks continuity, a story that connects the fleeting moments of life to a broader temporal pattern. As this segment draws to a close, the listener should feel the twin sensations that the idea of cyclic cosmology provokes: the squeeze of insignificance and the lift of continuity. Whether the Big Bang was an absolute beginning or a rebirth, the evidence accumulated so far gives a robust account of the universe's observable infancy. But the borders of that account remain permeable, inviting both theoretical inventiveness and empirical vigilance. The cosmos may be a single unfolding narrative, or it may be an ensemble of passages where conditions repeat, vary, and leave faint, salvable traces. The work of discerning which is true is ongoing, and it will demand instruments, patience, and the same humility that underlies every great scientific advance, an openness to being surprised. In the next passages, the focus will narrow from the cosmic background to the planetary archive, from the afterglow of a hot phase to the sedimentary pages of Earth, and the story will turn inward. There, the question was sharpened. If cycles leave traces, could a world as restless as Earth preserve anything of a previous eon? Or will the palimpsest be so thoroughly scraped that even the most ingenious of searchers comes up empty-handed, leaving only speculation and the ache of a question unanswered? The pursuit continues, and the cosmos waits, patient and immense. What is the cosmos, once thought to be coasting and cooling in a gentle wind down, had in fact begun to hurry away from itself. That single possibility space, not merely expanding but accelerating, arrived like an uninvited revelation and reshaped the future of everything that cares to look. It is a simple twist with enormous consequences, an extra push in the geometry of space that does not merely stretch distances, but redraws the map of what will ever be observable, what can be preserved, what stories may survive. The discovery of cosmic acceleration was not an abstract footnote. It was an invitation to reimagine endings. The observational story is tidy and human in its origin. In the late 1990s, two independent teams of astronomers chasing the faint blows of distant Type Ia supernovae found that those standard candles were dimmer than expected. In the language of light, objects at a given redshift appeared farther away than any model without acceleration would allow. The equations, when fed with this stubborn dimness, demanded an additional component to the universe's energy budget, something that acts like a repulsive gravity, pushing space to grow faster over time. This was the empirical shock. The theoretical response was immediate and intoxicating. If a mysterious energy fills space and resists gravitational collapse, then the long-term geometry and fate of the universe must be reconsidered. The simplest mathematical embodiment of this energy is the cosmological constant, a term the equations of general relativity admit, and that Einstein once called his biggest blunder before the observational pendulum swung back. As a vacuum energy, the cosmological constant exerts a uniform, unchanging pressure that accelerates expansion. But the cosmological constant also carries a stubborn philosophical problem. Its measured value, tiny as it is outrageously different from naive predictions of quantum vacuum energy. That mismatch is one of modern theoretical physics' sharpest knives, a number that seems finely tuned in a way that invites both suspicion and wonder. Beyond the cosmological constant lie other possibilities, dynamic fields that change over time, labeled collectively as dark energy by the community that seeks to bracket ignorance with a name. Quintessence, phantom energy, and other speculative constructs populate the theoretical landscape. They are distinguished quantitatively by an equation of state parameter W, the ratio of pressure to energy density. If W equals to 1, The behavior mimics a cosmological constant. If it deviates, the future unfolds differently. A value slightly greater than pi01 produces a slow, ever accelerating drift toward emptiness. A value less than Tine1 accelerates so aggressively that, in a finite proper time, bound structures might be torn apart in a metaphysical stretching that carries the terrifying name Big Rip. The emotional resonance of these alternatives is immediate. The prospect of a gentle, inexorable fading into darkness, heat, death, carries a bleak, contemplative melancholy. It is an ending that respects time's arrow and the second law of thermodynamics, a narrative where energy becomes increasingly unavailable and the universe grows colder and quieter. The Big Rip, by contrast, reads like a cosmic horror story written in equations, galaxies shredded, solar systems dissolved, atoms dissected as the scale factor diverges toward infinity in finite time. Either scenario insists on humility, but they differ in their dramaturgy. One is a slow, patient erasure. The other is a violent, finite crescendo toward nothingness. What matters for the present inquiry about deep time, about the palimpsest of Earth, about the possibility of civilizations lost to eons is not merely which fate obtains, but how acceleration changes the possibility of archaeological recovery and intergenerational continuity. Acceleration sets an effective horizon. Even now, as light from distant galaxies journeys toward us, there exists a cosmological event horizon beyond which events will never affect an observer because space itself expands faster than light can cross it. Over time, as acceleration continues, more and more of the universe slips beyond that horizon. The long-term picture is isolation. The local group, gravitationally bound, will remain a luminous island in an otherwise empty ocean, while galaxies beyond will recede, their light red shifted into oblivion. The lonely future this paints is not speculation from a distant mathematician, but a plausible, calculable pathway. Simulations project a universe where, in some tens of billions of years, clusters outside the local group will fade from view. In a few 100 billion years, most stars will have died. Star formation will sputter as gas is exhausted or ejected. By the time 1 trillion years have passed, galaxies will be darker, their stellar populations old and red. Black holes will dominate the energy budget of the few luminous remnants, slowly evaporating through Hawking radiation over stupendously long periods. Proton decay, if it occurs, would further strip matter from its present forms. Ultimately, if heat death is the verdict, the cosmos will approach a near-uniform soup of low-energy particles, a low-grade background noise where computation, memory, and life become ever more difficult. For those who imagine searching for signs of previous cycles or past intelligences, acceleration complicates hope. If the universe stretches so relentlessly that light and information beyond certain scales are forever irretrievable, then the cosmic record becomes not simply sparse but actively pruned. Traces that might once have been detectable gravitational wave imprints, radiation backgrounds, coherent structures on the larger scales can be diluted into undetectability. The accelerated expansion makes the cosmos a forgetful archive. It is not merely passive erosion, but an active widening of the gulf between cause and observer. Yet the story has wrinkles. Some models of dark energy are dynamic and may evolve. If dark energy decays or transforms in the future, the balance could tip. Acceleration might slow, stop, or even reverse, leading to new cosmological phases. In certain cyclic models, the current accelerating phase is a precursor to a transition that eventually seeds a new contraction and bounce. Penrose's conformal cyclic cosmology, for example, relies on a universe that expands to a cold, dilute state wherein massless radiation becomes the dominant content, enabling a mathematical rescaling to a fresh eon. But such exotic transitions depend sensitively on the behavior of dark energy and on deep, unresolved issues about entropy and information across cosmic epochs. Even if dark energy behaves as a pure cosmological constant, however, there are subtle ways remnants might persist. Quantum fluctuations, topological imprints, or tiny anisotropies frozen into the cosmic microwave background might yet encode histories beyond the hot phase. If the prior state of the universe left non-transient fingerprints, clever analysis could tease them out. To the extent that any such signatures survive an accelerating universe's dilution, they will be faint and demand instruments and minds of exceptional delicacy. This is where human timescales become acute. Humanity's current scientific window measuring the cosmic microwave background, surveying supernovae, Mapping large-scale structure exists in a particular epoch in which galaxies are visible and the cosmic web is richly detailed. Future observers in an ever-accelerating cosmos will have a narrower observational palette. They might infer a very different cosmology from ours, perhaps concluding that their island universe is everything there is. Their fossil record of distant structure would be truncated, their reconstructions necessarily impoverished compared to what is accessible now. That thought is both sobering and oddly urgent. The present moment is a privileged one for cosmology, a brief epoch when multiple lines of evidence cohere into a rich narrative about the universe's past. The implications for Earth and its long-term archive are no less stark. Cosmic acceleration will not meddle with planetary tectonics or biological evolution in the near term, but it participates in a larger account of cosmic habitability, the energy sources that nurture life stars, the cycling of elements. The dynamics of galaxies are transient phenomena in an accelerating universe. Star formation declines as the cold gas reservoirs that feed new stellar generations are exhausted or heated. The formation of new chemical complexity, the very furnaces that produce planets and their constituents, becomes less common as cosmic time marches on. In that sense, acceleration is an adversary to future richness. The longer the universe accelerates, the more it seals off pockets of creation, leaving fewer places where complex structures can arise anew. A further layer of reflection concerns information preservation over deep time. Even within a single eon, information can be scrambled, erased, or hidden. Geological recycling on Earth is relentless. Plate tectonics, erosion, metamorphism, and subduction lap away at the sedimentary pages of planetary history. In a universe that accelerates, the cosmic environment adds an extra filter. Suppose, for argument's sake, a previous cosmic cycle did leave technosignatures, artificial isotopic ratios, manufactured polymers, or engineered mineral assemblages. Accelerated expansion does not directly strip these traces from a planet, but it reduces the prospect of their being observable on cosmological scales. For civilizations that might wish to send messages across eons, acceleration is an enemy. It constrains the channels and time frames within which transmission and detection remain feasible. The practical response to these constraints is methodological. Observers attuned to the possibility of cosmic cycles or to the hunt for ancient intelligence turn to measurements that are robust under expansion. Isotopic anomalies in the oldest terrestrial minerals, entirely local yet ancient, become prime targets. Likewise, searches for unnatural ratios of long-lived radionuclides and lunar regolith or deep-sea sediments gain urgency. They are archives, less susceptible to plate tectonic recycling. On cosmological scales, gravitational waves become especially important. Unlike photons, low-frequency gravitational waves traverse space with different vulnerabilities to expansion. Certain primordial gravitational signatures could, in principle, preserve information about violent events preceding the hot phase. The development of detectors sensitive to nanohertz and lower frequencies through pulsar timing arrays and future space-based observatories thus becomes not merely a technical frontier, but a conceptual lifeline to prior histories. One cannot escape the philosophical contours that acceleration carves into thought. The human imagination gravitates toward narratives with beginnings and ends because those shapes structure meaning. Acceleration threatens to smudge the end into a long, featureless tale or to produce a violent terminal event with no moral of the story. Either way, it presses on notions of permanence and legacy. If civilizations are transient, and if the cosmos itself tends toward isolation, then the drive to leave durable traces becomes both more poignant and more pragmatic. The desire to seed information across timescales becomes an ethical project, not merely vanity but a response to a universe whose expansion erases more than distances. It erodes possibilities. Yet there is also a solace in scale. Acceleration, even as it separates islands of matter, makes the present moment a rare window of relational abundance. Galaxies are close enough to talk to one another across light years. The cosmic microwave background is bright enough to be mapped, and dissected primordial abundances are readable. The capacity to ask whether the universe has had prior lives, whether Earth's geology might hide technological ghosts, and whether civilization can be preserved against cosmic tides is itself an expression of a fleeting alignment, an occasion when resources, instruments, and curiosity coincide. If the universe is inclined to forget, then the act of remembering becomes a defiant, necessary art. In practical scientific terms, the acceleration discovery has altered research priorities. Surveys designed to measure dark energy's equation of state by mapping supernovae distances, baryon and acoustic oscillations. Large-scale structure and weak gravitational lensing seek to constrain W with ever finer precision. Laboratory experiments probe the vacuum, while theorists sketch frameworks where the cosmological constant is natural or where dynamic fields evolve in ways that reconcile observation with deeper microphysics. These are not ivory tower projects. They are the equivalent of forensic work at cosmological scales. The kind of detailed scrutiny that could determine whether the universe drifts forever, tears apart, or turns over into something new. As this segment closes, the listener should feel the double-edged clarity that cosmic acceleration brings. On one edge is the realization that the universe has agency of its own, a large-scale dynamical character that will determine what remains accessible and what will be forever hidden. On the other is the human responsibility to act within the narrowness of an epoch that is peculiarly well-suited to discovery. The accelerating cosmos does not extinguish curiosity, it sharpens it. It reframes the hunt for ancient voices and for possible prior worlds as a race against a vast and indifferent stretching of space. Whether the universe proceeds to a quiet, entropy-driven dusk, tears itself apart in a finite climactic rip, or cycles in some yet unimagined way, the present generation of detectives, astronomers, geologists, physicists holds the instruments that can, for a fleeting moment, pry open time's sealed hands and read what has been left there. The narrative will now, slowly, turn its attention even more inward, from the behavior of the cosmos on the grandest scales to the stubborn, noisy, and manipulable records stored in stone and bone. If cosmic acceleration narrows the cosmic horizon, then terrestrial archives gain a particular gravitas. The next chapters will examine what sediments, zircons, isotopes, and ancient shorelines may yet whisper about lives and technologies that once were, about what can be salvaged of a past, even if the universe itself begins to forget. What does an ending look like when measured in deep time, not as a headline, but as a slow arithmetic of energy, an accounting of entropy, a geometric change that reorders what can be seen and what can be remembered? The question has the quiet force of a moral parable and the cold rigor of a physics problem. In modern cosmology, three narratives stand out as the archetypal ways the universe might conclude its story: the Big Freeze, the Big Crunch, and the Big Rip. Each is an expression of the same equations being allowed to roam toward different asymptotic futures. And yet, beneath the mathematics, these scenarios carry very different sense of possibility, a patient extinguishing, a violent collapse, or a tearing so complete that even the atoms feel betrayed. For anyone interested in deep time, in the fate of planetary archives, and the potential survival of information across eons, these are more than esoteric endpoints. They are the metaphors that shape strategy and the constraints that shape hope. The Big Freeze, heat, death, is the most sober and classically thermodynamic of these fates. It is the long, inexorable march toward maximum entropy in which usable energy becomes ever scarcer. Galaxies march apart, star formation dwindles as cold gas reservoirs are exhausted or heated beyond the point of collapse, and the universe becomes a landscape of aging, red stars and quiet remnants. Over tens to hundreds of billions of years, the vibrant star-forming epochs of the cosmos taper off. White dwarfs cool into black dwarfs. Neutron stars and black holes remain as the last custodians of mass and information. Black holes, themselves, the universe's odd repositories, will slowly leak energy through Hawking radiation over stupendous timescales, durations so long that they have to be expressed in exponents upon exponents. If protons decay, a hypothesis not yet settled, then the very matter that composes planets and fossils will be subject to dissolution. Atomic structures will not be eternal. Emotionally, the Big Freeze reads like a quiet elegy. It is not dramatic in the sense of sudden violence. Rather, it is a slow attenuating of possibilities. For those who imagine preservation of knowledge across cosmic epochs, it is double-edged. On the one hand, the universe persists. Information need not be annihilated by brute force. Structures survive for a long time, and local repositories, a buried library in a geologically quiet region or a vault on an airless moon, might outlast civilizations by many millions of years. On the other hand, the universe trends toward a state where physical processes that enable life, computation, and the maintenance of complex systems become vanishingly rare. Energetic gradients flatten, heat engines stop being viable. In such a universe, the long-term survival of active memory and intelligences is challenged not by instant annihilation, but by the starvation of the very conditions that support persistence. The archive remains possible, but its custodianship must contend with an ever-diminishing ledger of usable energy. The Big Crunch, by contrast, is theatrical. In that scenario, the cosmic expansion stalls and reverses. Gravity regains control, and the great distances that had once stretched taut begin to collapse back together. Galaxies converge, temperatures climb, densities increase, and the familiar fabric of space-time curls toward a state that superficially resembles the conditions inferred for the early hot phase. The final contraction culminates in a singularity of the classical equations, a point where curvatures grow without bound, and where existing mathematics breaks down. The picture evokes closure, an undoing of expansion, a return to smallness. The emotional texture of the Big Crunch is paradoxical. For some, it is a cosmic closure that feels almost literary, an arc that returns to its origin, cutting the ribbon with unambiguous finality. For others, it hints at an opportunity for rebirth. The technical problem with this optimism is entropy. If entropy has increased during the prior expansion, how could a later contraction restore conditions suitable for low entropy initial conditions? Classical thermodynamics would say it cannot. Information disorder would remain. But theoretical work offers caves of possibility. Quantum gravity, the elusive synthesis that might reconcile the small and the large, could alter the rules. In certain formulations, the singularity is smoothed, and a contracting universe can rebound into a new expansion, giving rise to a bounce rather than absolute annihilation. If the bounce is possible, then the Big Crunch is not an end so much as a hinge, a mechanism through which information might be funneled, transformed, or partially preserved into a new epoch. Whether that preservation is feasible, or whether it is only an attractive metaphor, depends on physics not yet fully understood. Between these two sits the Big Rip, the most viscerally unsettling of the three. This scenario requires a particular sort of dark energy with an equation of state parameter less than ms1, what is sometimes called phantom energy. Its effect is not merely to accelerate expansion, but to do so at an increasing rate that, in finite proper time, sends the scale factor to infinity. The mathematical result is brutal. First, galaxy clusters are unbound. Then galaxies lose their coherence. Solar systems are disrupted. Planets are ripped from their orbits. Molecules are dissociated. And ultimately, even atomic nuclei and subatomic structures are pulled apart. The progression can be described on a timeline where progressively smaller bound systems are overcome as the repulsive effect of space's energy grows ever stronger. In short order, by cosmic standards, the universe accomplishes in a finite interval what entropy otherwise would take eons to achieve. The Big Rip carries the drama of an ending that feels both fast and inescapable. For planetary archives, it is devastating. The physical substrates that could store information, rocks, ice, metals, are forcibly dismantled. Preservation strategies that rely on physical durability are rendered impotent. The only conceivable repositories that might outlast such violence are those that are not made of bound structures, perhaps quantum correlations that somehow survive in a highly speculative way. But the plausibility of such survival is slender. The Big Rip is, in essence, an eraser that does not discriminate. It is an ending that raises the starkest question. If the universe can be rent apart at the level of atoms, what hope is there for any record to carry forward? It is worth pausing to emphasize that these scenarios are not metaphors only. They are consequences of dynamics that can, at least in principle, be constrained by observation. The behavior of dark energy, whether it is an immutable cosmological constant, a slowly varying field, or something stranger, is the central empirical question that distinguishes these futures. Current measurements favor an equation of state parameter near 1, consistent with a cosmological constant, which implies a gradual and persistent acceleration but not necessarily a rip. Yet observational margins and theoretical frameworks leave room for alternatives. Thus, the communal scientific enterprise becomes an investment in instruments and time, measuring the past light patterns of supernovae, mapping baryon acoustic oscillations, probing the cosmic microwave background, and listening for gravitational whispers that might betray deeper dynamics. Beyond the immediate physical mechanics, there is a deeper, almost metaphysical layer to confront. What does it mean for information to be preserved or lost across cosmic endings? This is where cosmology intersects with information theory, quantum gravity, and philosophy. The classical intuition is bleak. Entropy grows, coarse graining hides microstates, and the path to more disorder is preferred. But modern physics supplies more subtle possibilities. The study of black holes, for instance, reveals the tension between the classical picture of irreversible loss and the quantum insistence that information must be preserved in unitary evolution. The black hole information problem prompted proposals in which information is not destroyed, but rather encoded in subtle correlations of Hawking radiation, or preserved at horizons in ways that the holographic principle seeks to make precise. If black holes, the very structures that dominate late-time cosmic energetics in the Big Freeze, can hide and then slowly return information in scrambled forms, then the universe has mechanisms that blur the simple equation of destruction. Similarly, in bounce or cyclic models, the key question is whether information can survive a high-density phase. If a contraction compresses degrees of freedom into scales where classical description fails, quantum gravity may provide the bookkeeping. Some theoretical frameworks propose that what looks like a singularity is actually a phase transition where degrees of freedom reconfigure but are not necessarily obliterated. Analogies from condensed matter physics, where phase transitions can reorganize but not erase microstates in certain senses, fuel guarded optimism. Yet the work remains speculative and the burden of empirical evidence is heavy. From a terrestrial perspective, the prognosis of cosmic endings reframes the priorities of preservation and the kinds of traces worth seeking. If the future is a big freeze, a pragmatic strategy emphasizes redundancy and energy-efficient encoding. Durable isotopic anomalies, non-natural abundances of certain long-lived radionuclides, or mineralogical structures that require technological manufacture could survive for geologically long intervals. The moon and deep, cold regions of the outer solar system become attractive vaults because they are less subject to tectonic recycling. If the future holds the possibility of a big rip, then even these strategies may be futile. The problem is not geological recycling, but cosmological unbinding. If a big crunch or bounce is plausible and the most intriguing hope is indirect, designing information that can imprint on quantities likely to be preserved across a transition, perhaps global topological features, conserved quantum numbers, or correlations encoded in relic radiation, though what exactly falls into that class depends intimately on the physics of the transition. This logic pushes the scientific imagination toward the kinds of observables that are robust under a variety of end scenarios. On planetary timescales, the oldest and most chemically stable minerals, zircons that record isotopic ratios, ancient lunar regolith that avoids plate tectonics, or deep-sea ferromanganese crusts, become precious. On cosmological scales, the target shifts toward low-frequency gravitational waves and large-scale anisotropies. Gravitational waves have a special status because, unlike photons, they are less susceptible to certain kinds of scattering and absorption. A background of low-frequency gravitational modes could, in principle, carry information about violent events that predate the hot phase. Likewise, subtle, non-Gaussian features in the cosmic microwave background might betray preceding dynamics. These are slender threads, but they are the kind of threads that could survive if any survival is possible. Ultimately, the real lesson of contemplating the big freeze, big crunch, and big rip is humility. The cosmos enforces constraints that no single species can ignore. It imposes horizons, both literal event horizons that prevent access to certain regions of spacetime, and epistemic horizons beyond which inference falters. Yet there is also a defiant tenderness in the human response. The act of asking these questions, of designing ways to place durable marks upon the world or to read the faintest relics of an earlier universe, is itself an assertion of meaning against a backdrop of eventual decline or upheaval. The end, then, is not simply a terminus to be feared or a finale to be mourned. Within each scenario there are tactical implications and philosophical prompts. Heat death teaches patience and the value of energy. Frugal encoding, the big rip, demonstrates the vulnerability of all structures. To certain physical parameters, the big crunch opens the door to speculative continuity. If quantum gravity can be kinder than classical equations suggest. In every case, the inquiry draws attention to what can be saved and to what must be accepted as ephemeral. As the narrative moves inward from cosmic dynamics to the stubborn archive of Earth, this triad of possible endings reframes the questions that follow. What traces are worth searching for, and what strategies might render those traces legible? If any of the three fates is the universe's eventual claim, perhaps it will not be the ultimate eraser, but rather a threshold, a door that opens onto a new set of questions about memory, transformation, and the persistence of meaning. Or perhaps it will be the final chapter, leaving silence in its wake. Either possibility sharpens the duty of those who read and record, to listen carefully now, to store deliberately, and to understand that in the face of cosmology's great scales, the human act of remembrance is at once fragile and profoundly valiant. What if the final punctuation mark of one cosmic story had been smudged and reused as the opening line of the next? The image is at once disturbing and oddly soothing, not a creation ex nihilo, but a manuscript of universes, pages pressed together and reprinted with slight variations. That single idea, that the universe might be cyclic, that today's Big Bang could be yesterday's echo, reshapes the scale of curiosity. It forces a different posture toward evidence, toward preservation, and toward what it means to be a transient intelligence in a universe that may have remembered itself long before humans ever asked the question. The hypothesis of a cyclic universe is not one monolithic claim, but a family of ideas, each with its own grammar. Some versions picture a literal bounce, space-time contracts, reaches extreme density, and rebounds into expansion. Others imagine a collision of higher dimensional surfaces, an ekpyrotic event, creating a new hot phase that, from within, reads like a beginning. Still others reframe the passage of an entire eon into a different mathematical cloak, so an infinitely expanded, cold cosmos can be reinterpreted as the seed of a new hot era. What these models share in their different accents is the suggestion that the cosmic ledger may record earlier chapters in ways that could be read. If the right lines were known and the right tools built, there is immediate philosophical friction at the hinge of these ideas. Thermodynamics puts a heavy thumb on the scale. Entropy rises, disorder increases, the arrow of time points one way. How can a later epoch have the low entropy conditions that seem necessary for a hot, structured beginning? If entropy has been accumulating through countless eons, this is the technical and emotional heart of the debate. It is technical because any plausible cyclic model must demonstrate how the bookkeeping of entropy behaves across transitions. It is emotional because human intuitions about cause and origin, the comfort of a single starting point, are unsettled by an eternal metronome. Different proposals answer the entropy objection in different ways. Some invoke mechanisms that hide entropy behind horizons or concentrate it in structures that become irrelevant to the next phase. Others suggest that the degrees of freedom that carry entropy are transformed, redistributed, or become inaccessible, while a different set of variables resets. Penrose's conformal cyclic cosmology, for example, leans on a mathematical rescaling. If particle masses fade and black holes evaporate over vast timescales, the universe's final cold state becomes, under a conformal extension, a beginning for a new aeon. Ekpyrotic scenarios rely on dynamics in extra dimensions, while other bouncing models point to quantum gravitational effects that could smooth a would-be singularity and allow a contraction to carry forward correlations into a new expansion. The most concrete bridge between speculation and measurement is the search for empirical traces, the fossil record of cosmology. If cycles have occurred, they might have left faint, peculiar fingerprints embedded within the cosmic microwave background, the low-frequency hum of gravitational waves, or the statistical distribution of primordial objects. The cosmic microwave background is a remarkably precise fossil of the hot, dense era, and it is also a delicate canvas upon which primordial disturbances may have been painted or erased. Tiny anomalies, concentric rings, unexpected alignments, or deviations from statistical Gaussianity have been scrutinized for hints of prior dynamics. The work is painstaking because the sky is messy, foreground emission from our galaxy, instrumental systematics, and the statistical irreducibility of random fluctuations conspire to mask or mimic potential signals. Still, even the search itself shapes thought. It reframes telescopes and radio dishes as archaeological tools that excavate not bones but thermophotons. Gravitational waves offer a different and perhaps cleaner archive. Produced by violent, large-scale motion of mass energy, gravitational waves propagate through space with a robustness that photons sometimes lack. A particular spectrum of primordial gravitational waves might survive a hot Big Bang and carry the imprint of a preceding contraction or collision. Low-frequency gravitational modes, for instance, could, in principle, be fossil remnants of events far older than the photon background. They are subtle and challenging to detect, but they operate under different vulnerabilities than light. They do not scatter off plasma, and they are less subject to the absorption processes that rearrange electromagnetic signatures. Pulsar timing arrays, space interferometers, and ambitious future detectors are therefore not merely incremental steps in astronomy, they are instruments tuned to the memory of the cosmos. At the same time, The prospect of cycles invites a shift in the concept of archaeology. Traditionally, archaeology deals with the material traces of past lives, tools, pigments, structures. On planetary and cosmological scales, the analogous traces are isotopic anomalies, mineralogical assemblages, long-lived radionuclides, and patterns in large-scale structure. If a prior aeon spread seeding agents or left energy imprints, those would not necessarily be grand monuments. They would be slender clues embedded in otherwise natural processes. A non-natural abundance of certain isotopes in ancient zircons, an unexpected enrichment of transuranic elements in lunar regolith, or a puzzling set of spherules in deep-sea sediments could be the traces that survive geological erasure. The palette is necessarily modest. The longer ago the event, the more subtle and chemically subdued the signature must be to survive through metamorphism, subduction, and erosion. This leads to an acute humility about the kind of evidence that might be preserved. Earth is a palimpsest, in the literal sense. Tectonics recycles crust, heat, and pressure rewrite mineral records. Erosion scours shallow archives, and organic evidence decays rapidly on geological timescales. Even the moon, which lacks plate tectonics, is not invulnerable. Micrometeorite gardening, solar wind implantation, and impact gardening scramble surfaces over eons. The preservation problem redefines expectations. If universes have cycled, and if prior aeons left technologically generated artifacts, those artifacts are more likely to be chemical or isotopic fingerprints than intact machinery. The search therefore becomes an exercise in identifying anomalies that cannot be explained by known planetary processes. A striking consequence of this thinking is how it reorganizes priorities across disciplines. Cosmologists refine statistical analyses of the microwave sky and model the signatures different cyclic scenarios would impose. Gravitational wave astronomers widen their frequency bands and improve sensitivity to nanohertz and even picohertz waves. Geochemists interrogate the oldest minerals with ever higher precision, hunting for isotopic offsets or nucleosynthetic byproducts that break from natural patterns. Planetary scientists prioritize pristine samples, deep cores from ancient continental shields, returned regolith from airless bodies, and meteorites that preserve pre-solar grains. These are not isolated efforts. The detective work is inherently interdisciplinary. Clues in terrestrial rock might guide the parameters cosmologists seek in the sky, and unexpected anomalies in cosmic surveys might prompt new analyses of terrestrial archives. There is an emotional texture threaded through this program that is as important as its technical demands. The cyclical perspective compresses the feeling of human smallness and extends the possibility of continuity. On one hand, the implication that the cosmos may have cycled innumerable times diminishes humanity's claim to cosmic uniqueness. Civilizations, no matter how advanced, might leave only the faintest chemical echoes that are easily erased by deep time. On the other hand, the very idea that the universe might retain memory, that patterns or correlations could persist across eons, is consoling. It suggests a form of cosmic continuity that is less about individual survival and more about the persistence of relationships, conserved quantities, global topologies, and statistical imprints that whisper of prior structure. That whisper is what drives the patient rigor of modern science. There is a crucial difference between the poetic attraction of cyclical cosmology and the discipline of turning that attraction into testable predictions. The field demands falsifiability. A cyclic model must say concretely what observable difference it predicts from a single origin. Big Bang. Will there be rings of anomalous temperature in the microwave sky, a telltale spectrum in low-frequency gravitational waves, a specific abundance pattern of primordial black holes? Each of these is a hypothesis that can be checked, and each carries its own observational challenges. One of the most haunting practical lessons of the cyclic hypothesis is how it reframes the notion of legacy. If cycles make the universe forgetful, or if cosmic expansion progressively hides evidence, the human project of leaving a durable record becomes simultaneously more urgent and more modest. Grand monuments may be brittle, chemical encoding may endure longer. Yet even the most durable strategies must contend with planetary and cosmic processes beyond human control. Tectonics that recycle crust, cosmic expansion that redshifts and dilutes signals, and the entropic arrow that favors disorder. Thus, the ethic of preservation, in the face of deep time, becomes one of redundancy, of encoding information across multiple media and multiple locations, and of exploiting archival niches, cold, inert environments where change proceeds most slowly. There is also a subtle sociological shift embedded in taking cyclical cosmology seriously. It pushes for longer time horizons in research investment, patience in data collection, and an appreciation that some answers may require generations of instrumentation and cumulative cross-disciplinary work. That patience is not passive. It is a disciplined, forward-looking strategy. Build better gravitational wave observatories, refine calibration of microwave maps, and drill ever deeper cores. It is, in effect, a cultural choice to value the slow, cumulative work of detection over the vanity of quick spectacle. Finally, the cyclic idea reframes human meaning without resolving it. Whether or not universes truly cycle, asking the question expands the scope of imagination. It situates human life in a deeper, temporal context, invites new kinds of inquiry, and reframes preservation as both ethical and scientific imperative. The search for imprints of prior aeons is modest in its hopes but grand in its consequences. If a convincing trace were ever found, a non-natural isotopic signature millions of years old, a gravitational wave pattern inconsistent with single-bang inflation, or a coherent non-Gaussian feature in the microwave background that aligns with a predicted pre-hot epoch event, the implications would ripple through cosmology, philosophy, and the human sense of continuity. Until then, the task remains quietly heroic. The instruments hum, data accumulates, and models refine. Each null result tightens the bounds on what is possible and redirects the search. Each tentative anomaly raises the stakes and demands rigorous validation. The cyclical cosmology program is not a single grand sweep, but a mosaic of small, interlocking efforts, numerical simulations, detector design, isotope geochemistry, lunar and meteoritic sample analysis, and careful statistical inference. Together, these efforts form a kind of patient archaeology of time itself. In the end, the cyclic hypothesis offers a dual lesson. It imposes humility, an acknowledgement of how fragile and transient terrestrial records can be under the pressure of deep time. And it supplies resolve, a scientific commitment to listen carefully for whatever echoes remain. Whether the universe closes and reopens like a book, collides in higher dimensional spaces, or simply flows forward into an ever-expanding dusk, the search for traces is a testament to one species' brief capacity to wonder. That capacity may be small against the canvas of aeons, but it is precisely the instrument that can, in a rare and narrow epoch, pry open the possibility that the cosmos has been writing its own history for far longer than humanity has professed to read. Could the faint wash of microwaves that fills the sky be more than a fossil glow? Could it be a palimpsest, not of human ink, but of cosmic ink, carrying, in its subtle irregularities, the memory of events that predate the hot, dense epoch we call the Big Bang? That provocative question sits at the center of this chapter like a hinge. It is the kind of question that makes scientists lean forward in the dark, adjusts instrument designs, rewrites grant proposals, and, occasionally, sends the community into a brief collective fever. It is also the kind of question that forces patience. The signatures it posits are faint, the analyses are exacting, and the verdicts often arrive slowly and ambivalently. The cosmic microwave background, CMB, is the closest thing modern observers have to a fossil record of the early universe. It is a uniform sea of black-body photons at about 2.7 Kelvin, but embedded within that uniformity are ripples, temperature, anisotropies, and polarization patterns that encode information about density fluctuations, acoustic oscillations, and the imprint of quantum fluctuations amplified by cosmic expansion. For decades, those minute variations have been catalogued, mapped, and mined. Each new instrument, COBE, WMAP, Planck, has sharpened the image, revealing more texture and more puzzles. Within that growing detail lies the possibility that the CMB might contain anomalies that cannot be explained by the standard single hot phase model, anomalies that, if robust, could be read as traces of something earlier. The idea that the CMB could hold echoes of a prior cosmological epoch is not unmoored speculation. It follows from concrete, theoretical proposals. If the universe underwent a bounce, a brain collision, or a conformal rescaling from one aeon to the next, then certain classes of perturbations might survive the transition. These survivors are not likely to be grand, intact architectures, not intact technological artifacts or intelligible signals, but statistical and morphological irregularities, concentric patterns, localized hot or cold spots, non-Gaussian distributions of temperature fluctuations, polarization modes with unusual angular dependencies, or a background of low-frequency gravitational waves that refuses to fit the inflationary template. In short, the memory would be subtle and statistical, not literal and pictorial. The story of empirical searches for such imprints is a story of meticulous measurement and guarded exhilaration. In the early years of 21st century precision cosmology, a number of researchers scanned CMB maps for patterns that might betray pre-Big Bang phenomena. Some analyses claimed excesses of concentric rings, low-variance circles nested within the microwave sky. That seemed, at first glance, inconsistent with the expectations of a purely random Gaussian field. Other claims pointed to the so-called CMB cold spot, a region of anomalously low temperature that some argued could be the signature of a collision with another universe or a remnant of pre-hot dynamics. More recently, the idea of Hawking points, localized hotspots that might be the afterglow of evaporating black holes from a previous aeon, captured public imagination when proposed by proponents of conformal cyclic cosmology. Each claim ignited a familiar arc of scientific drama: initial excitement, rapid cross-checks by other groups, increasingly careful statistical scrutiny, and often revision or refutation. The history is instructive because it reveals how careful the community has had to be when reading patterns in the cosmic noise. The CMB is a finite dataset. There is only one sky to measure, and the statistical tools used to interpret it must respect that uniqueness. Look elsewhere: effects, foreground contamination from our galaxy, instrumental systematics, and the quirks of map-making can all produce illusory patterns. What looks like an exotic fingerprint can be, with a different choice of analysis or a better understanding of dust emission, merely a statistical fluke. The lesson is a methodological one. Extraordinary claims demand extraordinary rigor, and the line between pattern and parochial artifact is often thin. Yet the repeated null results and the frequent demotion of sensational claims do not extinguish the pursuit, they temper it. Scientists learn to translate romantic hypotheses into quantitative predictions that can be falsified. The question shifted from poetic possibility to concrete measurement. Does the CMB contain a statistically significant departure from Gaussianity in specific multipole ranges? Are there localized spots whose spectral signatures differ from cosmological blackbody expectation and from known astrophysical foregrounds? Do polarization maps contain B-mode patterns on angular scales or amplitudes inconsistent with inflationary gravitational waves alone? The instruments responded. Planck delivered all sky maps with unprecedented sensitivity and angular resolution. Ground-based arrays such as ACT and SPT carved deep, narrow windows into the sky. Polarization-focused experiments pushed into the delicate realm of B-mode detection. Each improvement reduced error bars and tightened the parameter space in which exotic imprints could hide. Crucially, these advances also improved an ancillary capability: the suppression of foreground confusion. Galactic dust, synchrotron emission, and extragalactic sources can mimic primordial features. Disentangling them requires multi-frequency observations, precise calibration, and rigorous modeling. The better the instruments, the sharper the scalpel that separates potential cosmic memory from local interference. But there is another channel of memory that bypasses electromagnetic complications: gravitational waves. Produced by violent rearrangements of mass energy, gravitational waves travel largely unimpeded across cosmic history. A spectrum of primordial gravitational waves could carry the imprint of a bounce, a collision, or other non-standard pre-hot events in ways the photons cannot. Low-frequency gravitational modes, the kind that would be targeted by pulsar timing arrays or by future spaceborne interferometers, could, in principle, preserve information about the largest scale dynamics that preceded the hot phase. Detecting such a background, characterizing its spectral index, and comparing it to what inflation predicts would be a powerful discriminant between single Big Bang scenarios and more exotic, cyclic or pre-Big Bang alternatives. This is why gravitational wave astronomy has become part of the same archaeological program as CMB studies. The two approaches are complementary. The CMB is exquisitely sensitive to certain scalar and tensor perturbations at the surface of last scattering, while gravitational waves can probe phenomena that interacted weakly or not at all with the primordial plasma. Together they form a cross-validated search strategy. If both channels were to hint at an anomaly pointing in the same direction, the argument would grow enormously stronger. Conversely, consistent null results in both channels would constrain the space of viable cyclic models sharply. The technical stakes reveal the emotional stakes. There is the thrill of potential discovery, the sense that, with patient measurement, humanity might pry open a window into errors previously thought inaccessible. That possibility fuels proposals, funding streams, and decades-long international collaborations. There is also the melancholy that comes with repeated disappointment, claims of detection that collapse under scrutiny, minute anomalies that fade with better data, and the creeping realization that some histories, even if true, may be undecidable with any practical instrument. The community oscillates between optimism and skepticism, and that oscillation is itself an engine of rigor. Beyond the immediate labors of detection lie subtler questions about what kind of memory the universe could carry and how that memory would be encoded. Inflation, if it occurred as commonly modeled, is an eraser in certain respects. A phase of exponential expansion stretches pre-existing inhomogeneities beyond the observable horizon, diluting their influence on observable modes. That is why many argue that inflation makes the prospect of seeing pre-inflation signatures in the CMB intrinsically unlikely. But not all cyclic models invoke an inflationary eraser. Some propose mechanisms through which correlations survive or are reintroduced. Brain collisions could imprint specific non-Gaussian features. Bounces mediated by quantum gravitational effects could seed a distinctive tensor spectrum. Penrose's conformal idea even suggests that certain black hole evaporation processes at the end of an aeon would leave localized imprints that might be visible in the early thermal maps of the next. Parsing these theoretical possibilities into observable tests is a demanding task. It requires not only high-fidelity data, but also careful modeling of how processes at Planckian or near-Planckian energy scales cascade into low-energy observables. It is an interdisciplinary endeavor. Cosmologists, particle theorists, statisticians, and instrument scientists all have to learn to speak the same language. From the statistical side comes caution. When a researcher claims an anomalous ring or spot, fellow analysts ask for independent pipelines, bootstrap tests, null maps, and simulations that reproduce the entire analysis chain. From the theoretical side comes humility. Many proposed signatures are highly model-dependent. A specific pattern that one theory predicts might not be generically expected across plausible parameter choices. The cultural choreography of this work matters. The field has learned to value replication and open data. Planck's public release of maps and analysis code enabled independent verification of surprising claims. That transparency turned what could have been a parade of unrepeatable headlines into a careful, self-correcting process. The social norms of verification are as essential as the instruments themselves. In a domain where the dataset is unique and the signals subtle, intellectual honesty and communal scrutiny are the true preservers of progress. If the cosmic background does contain memory, its discovery would have consequences that ripple far beyond cosmology. It would reshape philosophical narratives about origins and continuity. It would alter the way historians of ideas think about the search for legacy and memory across scales. For Earth's own long-term archive, a confirmed pre-hot imprint in the CMB would be a metaphysical consolation. Even if terrestrial geology has erased all trace of previous intelligences, the cosmos itself would have retained a whisper. Conversely, if the CMB remains stubbornly consistent with a single hot beginning, the philosophical pressure shifts. The absence of detectable cosmological memory strengthens the imperative to preserve locally and redundantly what intelligence can leave within the narrow windows that terrestrial and near-space environments offer. That imperative is not merely sentimental, it is practical. If cosmic memory is fragile or absent, then durable isotopic encodings, repositories on airless bodies, and redundant archives become the default strategies for leaving traces into deep time. If the cosmos preserves records across eons, then the hunt for cosmic fossils, in the microwave sky, in gravitational waves, in the distribution of primordial objects, is both scientifically motivated and existentially meaningful. The search for traces in the CMB is also bounded by temporal contingency. Cosmic acceleration narrows the observational horizon and reduces the palette of accessible information over extremely long timescales. The present epoch, when galaxies are visible and the cosmic web is richly detailed, is a privileged one for cosmology. Instruments built now and in coming decades will operate in that narrow window. If humanity is to exploit the cosmos as its archival medium, it must do so while the background still carries the imprints it seeks and while the universe's expansion has not yet rendered distant signatures irrecoverable. In the end, the task is equal parts technical and philosophical. It asks for better detectors, bolder collaborations, more rigorous statistics, and deeper humility about the limits of inference. It demands patience. The CMB cannot be rushed. Its faint features reveal themselves under long observation and careful subtraction of foregrounds. It calls for imagination disciplined by method. Speculative models must be translated into crisp predictions, and seductive patterns must be tested against the full rigor of modern data analysis. The cosmic microwave background remains, in many ways, a text half burned and half preserved. To read it properly requires exquisite instruments and a collective temperament tuned to both hope and restraint. Whether that text ultimately yields a clear sentence about previous universes, or whether it remains eloquent only about the hot epoch it most directly records, the pursuit itself reshapes the scientific enterprise. It extends archaeology into the sky and presses the human imagination to conceive of memory beyond the geologic. The next sections will turn from this grand celestial manuscript to the scraps closer at hand, the mineralogical and isotopic records on worlds and moons, the deep cores and zircons that might preserve technological whispers, and the reasoning that links small, local anomalies to the largest questions of origin and recurrence. The search for traces continues, proceeding from the broad, cold glow overhead to the dense, noisy pages beneath the feet. What would it mean to read the universe like a manuscript written in an alphabet that humans have only begun to decode? In one of the most audacious corners of theoretical physics, the letters are not merely the familiar particles and forces, but extended dimensions, vibrating strings, and membranes adrift in a higher dimensional sea. In that grammar, the Big Bang might not be a unique punctuation mark, but a footnote, one of many eruptions when extra-dimensional surfaces brushed and collided. The question here is practical as much as philosophical. If those collisions happened, what scars would they leave in the architecture of energy itself? What marks, subtle or bold, might survive inflation, expansion, and the long smoothing of matter into galaxies? These are the N marks in the energy structure, the discrete signatures written into fields, spectra, and space-time by events that preceded, accompanied, or even produced the hot epoch we call the Big Bang. M theory, the contemporary umbrella that binds various string theories, offers a picture both dizzyingly elegant and frustratingly distant. It proposes that the universe is not merely three-dimensional space plus time, but may include additional spatial dimensions, curled or extended in ways not directly perceivable. Within this framework, the familiar cosmos could be a three-dimensional membrane, a brain, embedded in a higher dimensional bulk. The bulk might host other brains. Their interactions are not merely mathematical curiosities, they can be dynamical. Collisions between brains, under certain conditions, have been shown in models to produce energy densities and temperatures akin to a Big Bang. In ecological terms, a brain collision is not an explosion in pre-existing space, but the sudden concentration of energies in fields where two extended objects intersect. There is an immediate, almost cinematic image here, sheets of reality sweeping past each other and, at the moment of impact, lighting into a hot, dense phase. But the interpretive leap is not aesthetic alone. Each such interaction would produce a cascade of effects, the excitation of fields localized on the brains, the liberation of energy into bulk modes, the generation of gravitational ripples, and the possible creation of defects, topological scars in the fabric of fields. The crucial question, the one that turns metaphysics into measurement, is this: which of those consequences would persist long enough and boldly enough to be read today? The first and perhaps most direct class of marks would be a distinctive gravitational wave background. A brain collision is a macroscopic, violent rearrangement of mass energy across distances that could be large compared to particle scales. It would produce tensor perturbations, gravitational waves whose spectrum, amplitude, and frequency content might be unlike those produced by standard inflationary scenarios. In practical terms, the energy cascade of a collision could seed low-frequency modes that survive the later plasma epoch, traveling mostly unscathed across cosmic history. Detecting a gravitational background with a spectral shape incompatible with single-field inflation would not prove a brain collision, but it would be a strong hint that something non-standard happened at the highest energies. Second, string-inspired cosmologies predict topological relics, cosmic strings, domain walls, or other defects. These are not strings in the everyday sense, but one-dimensional concentrations of energy that stretch across the universe and produce characteristic signatures. A network of cosmic strings, for instance, would create line-like discontinuities in the cosmic microwave background, produce gravitational lensing with unique patterns, and emit bursts of gravitational waves when loops oscillate and decay. The key is that these defects are persistent. They are not easily erased by later expansion. If present, they would be astronomical signposts, visible in precise CMB maps in surveys of lensing, or in the stochastic gravitational wave background. The discovery of such a relic would be an indelible mark in the energy structure, a fossil of field topology that outlives the thermal chaos that birthed it. A third category of marks lives in particle spectra, long-lived relics and excitations that do not belong to the standard model. Theory and related frameworks allow for excitations that escape into the extra dimensions or manifest as Kaluza-Klein towers, the imprint of motion in compact dimensions showing up as discrete mass states in four-dimensional physics. If the early universe populated such states abundantly, their decay products or residual populations could still influence cosmological evolution. Similarly, moduli fields, scalar fields of parametrized shapes and sizes of extra dimensions, can be displaced from their vacuum values during violent events. Their subsequent dynamics could leave footprints, transient modifications of expansion rates, localized inhomogeneities or specific patterns in primordial element abundances. The observational constraints are subtle but precise. Anomalies in particle abundances, unexpected contributions to dark radiation, or tiny temporal drifts in fundamental constants might be the whisper of such fields. Fourth, the collision of brains might have injected high-energy particles or triggered processes that leave chemical and isotopic scars. This is a bridge from the cosmic to the terrestrial. A sufficiently energetic pre-hot event could produce fluxes of exotic particles whose decay chains would alter isotope ratios in nascent dust grains, meteorites, or early formed minerals. On a planet, such injection could, in principle, be recorded in ancient zircon crystals or in deep lunar regolith repositories largely shielded from tectonic recycling. The signatures will be noisy, and disentangling them from astrophysical processes is hard. Still, the possibility is concrete. An anomalous abundance of certain isotopes or traces of heavy, short-lived nuclei that could not be produced by normal stellar nucleosynthesis might be an archival note of an extra-dimensional encounter. Fifth, and more abstract, is the prospect of altered correlation structure in primordial perturbations. Stringy dynamics concede non-Gaussian patterns, deviations from the nearly perfect Gaussian statistics that simple inflation predicts. These can take many forms: scale-dependent features, bispectra with particular angular dependencies, or localized deviations that align suspiciously with topological predictions. The cosmic microwave background remains the best laboratory for such searches because it literally records the primordial fluctuations in temperature and polarization. A detection of a specific non-Gaussian shape that matches a brain interaction calculation would be a kind of fingerprint, unique enough to suggest a particular high-energy mechanism rather than generic randomness. Sixth, extra-dimensional events might alter the spectrum of primordial black holes. Variations in the power spectrum at certain scales could preferentially seed compact objects whose mass distribution differs from what is expected under simple inflation. Primordial black holes are of dual interest because they are both probes of early universe small-scale power and potential dark matter candidates. An observed population with a mass function pointing to non-inflationary enhancement at certain scales might be read as a relic of a transient extra-dimensional influence. Each of these candidate signatures is a possible N-mark, one of many discrete imprints that could be written into the universes. Energy structure. But each faces a common antagonist: time and the processes by which the universe smooths itself. Inflation, if it occurred as in the standard picture, is particularly efficient at diluting pre-existing signals. Its exponential expansion pushes prior inhomogeneities beyond the observable horizon and tends to render any pre-inflationary memory inaccessible. This is the core technical tension. Brain collisions and other extra-dimensional events must either occur in a context that leaves some information in modes that inflation does not erase, or they must be contemporaneous with the onset of the hot phase in a way that imprints surviving features. Observationally, the path forward is methodical and multi-pronged. Gravitational wave astronomy now stands at the threshold of becoming a principal tool. Ground-based detectors open the window to transient high-frequency signals. Space-borne instruments and pulsar timing arrays push into the low-frequency domain where primordial and cosmological signals hide. A spectral detection inconsistent with inflationary expectations would be electrifying. Simultaneously, precision CMB polarization and intensity mapping refine constraints on non-Gaussianities and B modes, shrinking the parameter space where exotic imprints could lurk. Searchers for cosmic strings undertake lensing surveys, spectral studies, and gravitational wave burst hunts. On the terrestrial side, geochemists analyze the most ancient minerals with ever more precise isotopic instruments, planetary. Scientists prioritize pristine samples from airless bodies where surface gardening is slow and records are less scrambled. The emotional lens through which these efforts proceed is as revealing as the technical one. The scientific community moves with a mixture of restrained hope and rigorous caution. There is the private thrill at the prospect of finding a concrete trace that stretches human historical consciousness deep into pre-Big Bang times. There is also the habit of skepticism, honed by decades of null results and of seductive anomalies that withstood no independent scrutiny. The cultural temperament is therefore patient and collaborative, multiple instruments, multiple pipelines, multiple independent analyses. Science here behaves not as a feverish lottery, but as an incremental excavation, where every tentative hint is cross-checked and every extraordinary interpretation is tested against the cold arithmetic of statistics. Philosophically, the implications ripple wider than any data set. If collision events between brains are the mechanism that births hot epochs, then the cosmos may indeed be a rhythmic theater of births and deaths of entire universes, an ensemble of brains whose occasional meetings kindle new histories. This dismantles the metaphysical comfort of a unique origin and replaces it with a scaffold of possibility. Yet it also embeds human existence in a lineage broader than biological ancestry. The universe itself may be the inheritor of events preceding its thermal youth. There is both smallness and adventure in that thought. Smallness because humanity's temporal footprint shrinks against eons of cosmic rebirth. Adventure because the archival strategies change and science can aim with clarity and humility to retrieve fragments of prehistory. Practical constraints insist on a conservative operational posture. Any claim of extra-dimensional scars requires concordant evidence across channels. Gravitational waves that refuse to fit the inflationary template, CMB anomalies with robust statistical support and multi-frequency foreground subtraction, isotopic anomalies that withstand geochemical scrutiny and contamination hypotheses, and astrophysical signatures such as unexpected lensing or primordial black hole distributions that cannot be readily explained by known processes. No single line of evidence will likely suffice. The story, if it exists, will be woven from many slender threads. It is worth underscoring the difficulty without allowing it to become defeatist. The universe is not obliged to make its deepest history easily readable. Physical processes, expansion, thermalization, horizon growth, and entropic increase act like erasers. Yet physics is also merciful in other ways. Certain modes of information, topology of fields, conservation laws, tensor perturbations are more robust than the messy particulars of matter distributions. The theoretical work, therefore, is to identify which aspects of a brain collision or extra-dimensional event are durable in the face of cosmic evolution, and then to design observations optimized to those durable signatures. Finally, there is an ethical, almost elegiac dimension to this enterprise. If the cosmos bears marks of pre-hot epochs, the discovery will reshape narratives of origin, continuity, and meaning. If it does not, the result is no less profound. An absence of detectable prehistory would emphasize the precariousness of the present observational window and the urgency of preserving knowledge in places and forms least vulnerable to geologic and cosmological erasure. Both outcomes converge on a lesson about stewardship, whether the marks exist in the energy structure or not. The act of searching binds humanity to a project of careful listening, a willingness to let instruments translate whispers into claims, and to let caution govern the leap from data to story. In the end, the investigation of string theory and extra dimensions is not simply an esoteric theoretical pursuit. It is a mode of cosmic archaeology. It treats energy, fields, and the geometry of space as repositories of history and asks what can be read in them. The end marks, the possible scratches, kernels, and scars are hypotheses built from which mathematics and constrained by the blunt arbiter of observation. To seek them is to accept both the grandeur of possibility and the humility of uncertainty. To imagine that universes can be born of membrane collisions and to dedicate decades of careful measurement to deciding whether. That imagination corresponds to the marks the cosmos actually made. What if time were not a straight arrow but a loop, a circle folded upon itself, an endless ring of beginnings that were also endings? That single image commits the imagination to a different grammar. It asks not where things began and where they will end, but which moments repeat, which patterns survive, and what it means to be a brief observer inside a returning melody. If the cosmos is cyclic in a literal sense, then causality, memory, legacy, and meaning all acquire altered textures. The consequences reach from the deepest theoretical scaffolding to the gritty work of geologists and the quiet strategies of preservation. The idea that time might be nonlinear is not merely a poetic flourish. It has several precise faces in physics and mathematics. Poincaré proved, in a limited and idealized sense, that a finite, isolated system will, given enough time, return arbitrarily close to some previous state, a recurrence in phase space. In thermodynamics, however, the arrow of time is embodied by entropy, the statistical tendency for systems to evolve toward more probable, disordered configurations. These two facts press against each other. Recurrence theorem tells a mathematical tale for closed systems. Thermodynamics tells a statistical, empirical tale for real, macroscopic systems interacting with the environment. Their reconciliation, or the failure to reconcile them, is the hinge upon which looped time cosmologies must pivot. Modern cyclic proposals come in many flavors. Some are literal bounces. Contraction compresses space-time until quantum gravitational effects reverse the collapse into an expansion, a new hot epic, replacing what classical equations would call a singularity. Some are collision stories where higher dimensional brains brush and ignite a hot phase on their three-dimensional world. Others are conformal. The cold, dilute end of one eon is mathematically rescaled to the hot beginning of the next. In each version, the ordinary chronology dissolves into rhythms: contraction, expansion, collision, aftermath, fade, rescale. If any of these are true, then time may be segmented into aeons, long stretches with their own thermodynamic trends, and the human sense of before and after becomes a local narrative within a much grander pattern. What does nonlinear time mean for memory? If the universe cycles, can information survive the sweep from one eon to the next? This question pivots on what physical quantities are conserved or robust against the violent processes that typically accompany cosmological transitions. Some degrees of freedom are more durable than others. Topological properties of fields, defects, non-trivial winding numbers, persistent correlations can, in principle, be long-lived. Tensor perturbations, gravitational wave spectra, and conserved charges move through cosmic epochs with different vulnerabilities than do thermalized photons. In scenarios where a transition is smooth at the quantum gravitational level, correlations could conceivably thread across the bounce, carrying subtle imprints into the newborn expansion. The cosmic microwave background, already a primary archival medium for the hot phase, becomes a natural place to look for such imprints. But inflation, if it occurred, is a robust eraser. Exponential expansion dilutes information that is not expressed in modes that later re-enter the observable horizon. Hence, any trace that survives a bounce and later inflation must either be encoded into the very modes inflation amplifies or be produced after inflation has run its course. Gravitational waves, less hampered by plasma interactions than electromagnetic signals, provide a complementary channel. Low-frequency gravitational backgrounds could encode large-scale dynamics from pre-hot epochs in ways the CMB does not. The search, therefore, becomes a cross-disciplinary pursuit. Map the microwave sky with exquisite fidelity. Listen for stochastic gravitational backgrounds across frequency bands, and interpret anomalies with rigorous statistical frameworks. On a planetary scale, the problem is both simpler and crueler. Geological processes are efficient erasers. Plate tectonics recycles crust into the mantle, erosion smooths surfaces, metamorphism and high-pressure heating reset mineral. Structures, weather, and oceans dissolve fragile evidences of technology. The older the epoch, the more likely that any macroscopic artifact has been ground to dust. Yet not all records are equal. Isotopic patterns locked into resistant minerals, long-lived radionuclides in protected reservoirs, and the chemistry of ancient zircons preserve evidence across eons. The moon and many airless bodies also act as slower-changing repositories. Their regolith accumulates impact spherules and implanted particles over timescales that far exceed terrestrial erosion. Meteorites retain pre-solar grains and nucleosynthetic anomalies. If a past aeon left chemical fingerprints, a cocktail of isotopes non-trivial to reproduce by natural processes, then a diligent, patient analysis might detect them. The logic of preservation in a cyclical cosmos refines into a practical triage: what to encode and where. Information encoded in the fine structure of fundamental fields or in conserved quantum numbers might pass through cosmological transitions more readily than macroscopic constructions. On planetary scales, information encoded in the ratio of isotopes of long-lived elements, or locked within exceptionally durable mineral lattices, is more likely to survive tectonic upheaval. Spatial distribution matters. Airless moons, deep lithospheric pockets, and polar ice cores act as archives with different vulnerabilities. Redundancy across media, geological, astronomical, and maybe quantum, is the evident strategy. If time is likely to loop, redundancy is not merely prudent. It becomes the only plausible defense against the slow violence of natural turnover. Philosophically, loop time does a slow unraveling of certain comforts. The idea of a unique origin, a single first cause, loses its favored status when beginnings are seen as recurring local features of a larger, repeating process. Uniqueness gives way to statistical typicality, being one instance among potentially infinitely many realizations. That shift has emotional textures. For some, it is deflating. Uniqueness has been a scaffold of meaning for generations. For others, it is consoling. Recurrence implies continuity beyond ephemeral individuation, a cosmic persistence that carries form through transformations. Both responses reveal how tightly human narratives of identity and purpose align with linear temporality. Another sobering implication concerns the problem of duplicates. If the cosmos is truly cyclic and sufficiently large or infinite, then thermal fluctuations over arbitrarily long intervals could produce, by chance, configurations identical or nearly identical to ones observed before. Boltzmann considered such statistical recurrences and raised a paradox. In an eternal universe in thermodynamic equilibrium, rare fluctuations could spontaneously create observers. Boltzmann brains with illusory memories of a past that never existed. The resulting reasoning undermines the explanatory power of cosmological models that allow too much random resurrection of observers. Contemporary cosmology therefore pays attention to measure problems and selection effects. A cyclic cosmology must ensure that typical observers arise in histories consistent with robust statistical inference. Otherwise, the model risks self-undermining paradoxes where ordinary histories are swamped by random flukes. A related tension concerns causation and free will. If time loops in a literal sense, and if the universe cycles identically or near identically, then questions arise about determinism and novelty. Does recurrence mean repetition down to individual choices, or is each incarnation a variant? Most physically plausible cyclic models permit variation. Entropy, quantum fluctuations, and environmental contingencies conspire to produce divergence between cycles. The loop is then not a perfect repetition, but a template for variance. It suggests a world where themes reappear but with ever-shifting details, continuity without stasis. For human meaning, that may be a richer narrative. Patterns persist, but novelty remains possible. Scientific methodology itself must adapt to the possibility of loops. The search for pre-aeon imprints becomes an exercise in identifying robust, model-independent signatures, those features that cannot be easily erased by plausible transformations. Topology, conserved charges, and certain classes of tensor perturbations become prioritized because they are less likely to be thermalized away. On planetary levels, robust geochemical anomalies demand high-precision isotopic measurements, cross-comparison between terrestrial and extraterrestrial samples, and careful accounting for contamination. The work is painstaking. A hint in a microwave map or an odd isotopic ratio in a zircon is not a discovery until it survives the gauntlet of cross-validation, independent replication, and theoretical plausibility. Emotion shades these methodological choices. There is an ache in the recognition of the fragility of records, a humility that scientific patience must accompany. There is also a thrill that comes from the possibility of recovery, the idea that, by listening carefully and by building instruments of unprecedented sensitivity, fragile whispers from past aeons might be amplified into intelligible notes. That thrill fuels collaborations that span generations, observatories planned with century-long horizons, sample return missions designed to bring back the most pristine matter, and theoretical programs that attempt to translate the highest energy physics into low-energy observables. The human story embedded in these projects is one of deferred gratification and collective memory-making. Yet realism must temper ambition. Even if the cosmos cycles, the odds that a macroscopic, technological civilization leaves a straightforward, legible monument to future eons are low. Natural processes tend to randomize and to erase. The long-run survivors are the subtle, the chemical, and the topological. The search for techno-signatures across eons, thus, privileges the faint and the enduring, isotopic ratios inconsistent with natural nucleosynthesis, anomalous transuranic assemblages, mineral microstructures unlikely to form without directed processing. On cosmological scales, the search privileges patterns that encode large-scale correlations, non-Gaussian features in the CMB, a stochastic gravitational wave background with a distinctive spectral slope, anomalies in the mass function of primordial compact objects. These are difficult objectives, but they are not impossible. They are the sorts of problems that reward patient accumulation of data, relentless scrutiny of systematics, and cross-disciplinary triangulation. There is also a practical urgency imposed by cosmic acceleration. If the universe continues to accelerate, horizons will grow and accessible information will shrink. The privileged observational window in which galaxies can be seen and distant structures mapped is a narrow epoch relative to cosmological timescales. In a universe that slides toward isolation, the ability to read the cosmic archive is temporally bounded. The combination of cyclical speculation and accelerating expansion reframes priorities. Discover what can be discovered now, place durable archives where they are most likely to survive, build instruments that exploit the present richness of the sky. The metaphor of a palimpsest returns here with renewed force. Sheets of text once inscribed and overwritten, faint traces of earlier handwriting visible only under new light, capture the essence of cyclical time. The cosmos, geological layers, and human artifacts are all palimpsests of varying resilience. Reading them requires tools, telescopes, spectrometers, statistical techniques, and a temperament that balances hope and restraint. It requires an epistemic humility, the recognition that absence of evidence is not evidence of absence when processes of erasure operate relentlessly. It also requires courage, the willingness to fund long projects whose fruits may not be realized in a single lifetime, and to accept that the most profound answers may be couched in subtle, statistical patterns rather than dramatic monuments. Finally, the idea of an endless loop of time reframes what it means to be stewards of information. Whether cycles repeat identically or mutate from one eon to the next, the ethical stance remains: if knowledge and meaning have value, they deserve redundancy, care, and distribution across modalities. Encoding in geology, in orbit, in multiple forms of matter and field, hedges against the myriad processes that can erase any single repository. Such stewardship is not only a technical endeavor, but a moral one, a collective commitment to extend the reach of curiosity. Beyond the brevity of lives and civilizations, the question that began this passage, what if time were a loop, does not yield a simple verdict. Physics provides mechanisms that could underwrite looping, but also thermodynamic and observational constraints that make literal, identical recurrence unlikely. The balance between these forces produces a spectrum of plausible realities, from cycles that vary and carry faint memory to ones that are effectively irreversible in their consequences, to cosmologies where recurrence is mathematically possible but empirically irrelevant. Within that spectrum, the human task is clear and urgent. Listen with the best instruments available, map the sky and the rarest minerals with patient rigor, design preservation, strategies aimed at the most durable carriers of information, and carry forward an ethic of redundancy and humility. Time as a loop is not merely a metaphysical curiosity. It is an operational challenge for science and stewardship for civilization. It compresses the grand questions about origin and fate into actionable priorities about measurement and preservation. Whether or not the universe has already rehearsed these scenes many times, the act of asking binds humanity to a larger enterprise. To be careful readers of the palimpsest, to be patient excavators of cosmic memory, and to be conscientious authors of a record that, if anything, will increase the odds that some future aeon, or some inscrutable observer, will find what was left behind. What if the secret that ties one aeon to the next is not a dusty relic in some crustal seam, nor a pattern in leftover photons, but an invisible conductor that has been quietly shaping the whole performance from the wings? The notion is seductive because it anthropomorphizes the cosmos, a hidden force, patient and inscrutable, setting tempo and crescendo. Dark energy. This term that began as a placeholder for the universe's accelerating expansion has, in some speculative accounts, the quality of a maestro. It is not merely a background inconvenience to be measured, it is the agent whose behavior determines whether the cosmic symphony dwindles to a single pianissimo, tears itself apart, or folds back to begin another movement. There is a peculiar intimacy to thinking about dark energy this way. In ordinary life, a conductor does not create the instruments, it coordinates them. Likewise, dark energy may not manufacture matter or light, but its presence or variation scopes the large-scale history in which every other process, star formation, black hole growth, the survival of information takes place. If dark energy were constant, inert, and featureless, the cosmos would be set on a straightforward course determined by that fixed pressure. If, instead, it is dynamic, evolving, coupling to other sectors, capable of changing sign or intensity, then it becomes an active participant in cyclical scenarios. The difference is not merely poetic. It is the difference between a universe whose end is a slow fade and one whose end is a hinge capable of producing a new beginning. The physics language for this is familiar and stubbornly precise. In the simplest model, dark energy is a cosmological constant, a uniform, unchanging vacuum energy that exerts negative pressure. Its effect is measured by a number. The equation of state parameter W that, if equal to W1, reproduces the cosmological constant behavior. But one can imagine scalar fields with potentials, landscapes in which the field slowly rolls, oscillates, or tunnels. In such scenarios, dark energy is not fixed, it evolves. The field's trajectory across its potential can change the balance of expansion and contraction. If a field slowly decays, it can reduce repulsive pressure and allow gravity to reverse the expansion. If it climbs or flips sign due to coupling with other sectors or due to quantum transitions, it can drive phases of contraction that compress space-time toward an energetic pivot. In other formulations, dark energy is phantom-like. Its pressure is so negative that expansion accelerates with increasing ferocity, driving a catastrophic unbinding. In still others, it is ephemeral, a weather pattern in the vacuum capable of ebbing and flowing across cosmological epochs. Each of these behaviors has consequences for how cycles would operate. A dynamic, dark energy that decays or changes sign can be the trigger of a turnaround. The cosmos expands. Dark energy weakens or transforms. Matter and radiation's gravitational pull reasserts itself. Contraction follows. And some mechanism at extreme density, quantum gravity, extra-dimensional dynamics, or conformal rescaling, smears or reformats the state into conditions suitable for a new hot phase. In that picture, dark energy is the metronome. It sets the length of the expansion, it times the pause, and it cues the collapse. In ekpyrotic or brain collision models, similar roles are played by interbrain potentials. In conformal cyclicity, the role of dark energy-driven expansion is to create the cold, dilute environment that, under mathematical rescaling, can become the low-entropy seed of the next cycle. The argument for dark energy as a controller of cycles is not metaphysical fancy. It is a demand placed by thermodynamics and by the empirical fact of the present acceleration. If a cosmos cycles, entropy must be addressed. A naive, repeating universe would seem to violate the second law. How could low-entropy beginnings recur? A manipulable dark energy opens a route. If, in the late phase of an aeon, dark energy drives not merely expansion but a transformation that disperses and isolates entropy into structures that are effectively removed from the degrees of freedom of the emergent eon. If black holes evaporate fully, if mass becomes negligible, if horizons swallow certain sorts of entropy, then the door opens for a transition that does not merely shuffle noise around, but genuinely alters the entropy accounting. Whether nature permits such bookkeeping tricks is an open question. It depends on physics at scales where quantum gravity matters. But the surprising discovery that the universe is accelerating invites this possibility. Something with global reach is already influencing the cosmic ledger. That leads, in turn, to concrete observational stakes. If dark energy is the conductor, its score must show up in the music. The scientific program thus focuses on measuring numbery W, 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 the equation of state parameter as a function of time, and on searching for deviations from the pure cosmological constant behavior. Small, systematic drifts could be the fingerprints of a slowly rolling field. Sudden features or transitions in the expansion history might hint at phase changes in the vacuum sector. The large-scale distribution of galaxies, the pattern of baryon acoustic oscillations, weak lensing maps, and the precise distances of supernovae are all chapters of that score. Each instrument, survey, and long-term mission is like an ensemble reading the same part. They must harmonize to distinguish a faint dynamic from instrumental noise and astrophysical confusion. But the role of dark energy in cycles is not only to initiate expansion or contraction, it is also to control the survivability of imprints. An accelerating phase can be an eraser. It dilutes signals, pushes them beyond observable horizons, and renders correlations inaccessible. If dark energy grows, the universe becomes forgetful. Signals that might once have traveled and seeded new regions are stretched thin. Conversely, If dark energy decays or reorganizes in a way that concentrates or funnels information into protected degrees of freedom, topological features, long wavelength gravitational modes, conserved charges, then traces of prior epochs might be preserved. The trade-off is stark. The same actor that can enable a cyclical rebound can also obliterate memory unless certain channels are resilient to the stretching. That is why gravitational waves, topology, and conserved quantities loom large in strategies to detect pre-aeon imprints. There is a quiet urgency to this line of work because the present epoch is singularly favorable for cosmological archaeology. Galaxies are still visible. The cosmic web is richly detailed. Relic radiation and large-scale structure are accessible to mapping. If the cosmos is indeed orchestrated by dynamics that will eventually render far regions unobservable, then the current generation of instruments has a privileged window. The decision to build more sensitive detectors, to extend frequency bands for gravitational wave observation, and to launch long baseline experiments is therefore not merely about curiosity. It is a race to read the score before increasing expansion hides entire pages. Parallel to the conductor metaphor is another, darker possibility. What if the most decisive move of dark energy is to create a twin and inverse sketch of the cosmos that unfolds with reversed temporal orientation? The twin universe concept arises from a variety of theoretical provocations. A striking instance posits that the Big Bang might be the common origin of two complementary universes, one in which time flows forward as humans experience it, and another in which time, as a macroscopic ordering, runs the other way. The twin could be matter reversed, antimatter dominated, CPT mirrored, or otherwise opposite in symmetry. In such constructions, the two universes are not disconnected fantasies, but part of a single, larger state whose initial condition at the hot phase entangles or correlates them. The motives for considering a twin cosmos are both aesthetic and explanatory. A symmetric pair can address certain puzzles, the origin of the matter. Antimatter asymmetry, for instance, might be recast as a balance between two sides. A time-reversed twin could, conceivably, restore global CPT symmetry in a way that a single asymmetric universe cannot. In some proposals, the twin is born in a way that explains why the local arrow of time points as it does. The direction of entropy increase in each branch is locally consistent, but globally the pair forms a neutral or balanced whole. What would such a mirror universe mean observationally? The immediate answer is frustratingly minimal. If the twin is truly causally disconnected, then it is functionally invisible. Its existence would be a theoretical neatness without empirical consequence. But some versions of the idea permit subtle inter-universal correlations. For example, if the two branches share pre-hot correlations, entanglement across degrees of freedom that are not perfectly decoupled, the residual might show up as small, atypical statistical anomalies in the cosmic microwave background, as correlations in the stochastic gravitational wave background, or as peculiarities in the distribution of primordial perturbations. In another class of models, the twin's presence could be implicated in the apparent baryon asymmetry by positing that conserved. Charges are balanced between the two branches. The apparent excess of matter on this side is mirrored by an excess of antimatter on the other. From an observational point of view, the hunt is necessarily indirect. The twin universe hypothesis gains traction not by the spectacle of an interuniversal postcard, but by its capacity to make testable, albeit subtle, predictions, a distinctive spectrum of primordial gravitational waves, non-standard polarization patterns in the microwave sky, small non-Gaussianities with particular shapes, or unexpected correlations among neutrino backgrounds. Each putative signature must be disentangled from astrophysical sources and instrumental artifacts with extreme care. The challenge is heightened by the uniqueness of cosmological data. There is one sky, one story, and a million ways to misinterpret statistical quirks as profound implications. The philosophical and existential consequences of a twin universe are profound. If this cosmos is one of a pair, the human sense of solitude in time and space shifts. The notion of origin becomes relational. This universe is not the unique first instant, but one branch of a bifurcation. Meaning, designed as a narrative that centers a single sequence, loosens into a narrative that accepts duality. For some, the possibility offers consolation, continuity extended beyond conventional borders. For others, it complicates questions of legacy. If the total system balances itself in symmetries that erase net asymmetries, then attempts to inscribe a lasting, one-sided legacy may be cosmologically muted. At the level of practical thinking, the twin universe idea reframes preservation and detection strategies. If correlations between branches are possible only through specific modes, say long wavelength tensors, then investments in detectors sensitive to those modes acquire new urgency. If balancing charges are exchanged or shared at the earliest moments, then high-precision measurements of primordial abundances, neutrino asymmetries, and the low multipoles of the CMB become crucial. The complexity of the models insists on a diversified observational portfolio. Map the sky across frequencies, listen for gravitational hums at complementary bands, and probe the oldest, most stable geological archives on planetary bodies that resist recycling. There is an ethics to such a strategy as well. Whether or not a twin exists, the project of looking deep and asking precise questions strengthens the scientific infrastructure. That preserves knowledge against entropy and cosmological forgetting. Instruments built to test exotic ideas also produce data of practical value, maps of structure that guide galaxy formation theory, catalogs that illuminate the history of star formation, and geochemical surveys that sharpen understanding of Earth's deep past. Philosophically, the search for a twin universe and for the role of dark energy in cycles more generally carries a twin purpose. It is at once an attempt to reconstruct the cosmos's deepest turns and a rehearsal in humility. Humans, brief narrators in deep time, must learn to read faint inscriptions and to accept that the most decisive answers may arrive as whispers, not proclamations. In contemplating dark energy as a conductor and a twin cosmos as a mirror, the listener is invited into a patient, deliberate form of inquiry. The stakes are large: origin, fate, continuity, but the methods are modest and exacting. Measure time dependence of W with increasing precision, expand gravitational wave sensitivity to capture the faintest. Low-frequency background, extract the purest maps of primordial photons, and scrutinize the oldest minerals and the most pristine. Extraterrestrial regolith for isotopic oddities. Work across disciplines, build redundancy into archives, and preserve data with a mind toward geological and cosmological vicissitudes. The image that returns, inevitably, is both small and vast. On the one hand, dark energy is an arcane parameter in equations of state, a number that might shift by a mere fraction and yet determine the cosmos's large-scale choreography. On the other, that tiny number is the difference between a single slow fade and an astounding cyclicity in which eons unfold, collapse, and renew. Whether dark energy is the hidden maestro or a passive backdrop, whether the universe has a twin that reflects its beginning, these questions pull the human gaze outward and inward at once. They demand patience, instruments, and a willingness to accept subtlety, and they remind the audience of an abiding truth threaded through deep time thinking. The cosmos is at once stranger and more intimate than first impressions allow, and the act of listening, measuring, preserving, and reasoning is itself a way of keeping time with a universe that may have existed, in one sense or another, countless times before. What if every cosmic return left not only a new page in physical reality, but a faint, transposed line in a neighboring volume, a residue that seeped into a parallel universe and, through subtle channels, threaded itself into human myth, religion, and the gut-level sense that time is older and stranger than immediate perception allows? The idea sits at the intersection of physics and poetry, an audacious claim that repetition on cosmological scales could leak small, legible fragments of prior cycles into forms of existence that are adjacent to, but not identical with, the familiar world. It is a question that rearranges both the search for empirical signatures and the way a culture listens to its oldest stories. The proposition has two parts. First, there is a physical plausibility. In many theoretical frameworks, the universe is neither unique nor perfectly self-contained. Bubble universes nucleate in inflationary landscapes, brains collide in higher dimensional bulks, quantum branches multiply in Everettian splendor. In such pictures, a single hot epoch, the Big Bang as observed from within one causal patch, may be one realization among many. Some of these realizations may be near twins, differing only by slight parameter shifts. Others may be wildly different. The second part is anthropological. Humans everywhere carry a repertoire of motifs: floods, fires, twins, cycles of dying and returning, motifs that recur with an uncanny frequency across cultures isolated from one another. Are these motifs merely the predictable byproducts of shared environments and similar cognitive architectures, or could some of them be cultural fossils, echoes of events that, in a deeper cosmological sense, actually happened in an adjacent instantiation of reality? To treat this question responsibly requires two tempering moves. One is epistemic humility. The burden of proof is high. Extraordinary claims must rest on extraordinary evidence. The other is imaginative rigor. Plausible mechanisms must be sketched in detail and then tested. In the space between, a disciplined, speculative program can be articulated, one that connects high-energy cosmology to paleogeology, to comparative religion, to cognitive science, and to precision measurement. The project is not to convert myth into history, but to ask whether certain patterns in culture and matter might plausibly be the sediment of truly ancient, supracosmological processes. The physics that makes residue plausible begins with how information can survive transitions. A naive picture of cycles might say contraction, singularity, new expansion, and memory is erased, but modern thinking offers subtler arithmetic. Topology, conserved charges, and correlations carried by tensor modes are not necessarily erased by thermalization. They can pass through phases in disguised or redistributed forms. In several classes of psychic or bounce cosmologies, degrees of freedom that do not thermalize, for example, long wavelength gravitational modes or topological defects, can act as carriers. Similarly, in brain world scenarios, the intersecting dynamics can excite modes that are localized near the brain and hence survive the subsequent evolution in forms that influence the emergent fields of the new aeon. In quantum cosmology, entanglement and the subtleties of decoherence mean that a prior branch of the universal wave function might leave statistical correlations in the posterior distribution of fluctuations. These possibilities are technically delicate, but they are not logically impossible. Beyond the abstract, there are physical channels by which residues might reach a form interpretable by life and culture. Low-frequency gravitational waves are a prime candidate. They traverse cosmic history with relative immunity to scattering and absorption. If a pre-hot epoch featured large-scale rearrangements, brain collisions, bounces with anisotropic stress, or violent topological reconfigurations, the resulting tensor spectrum could be imprinted on the primordial gravitational background. Those imprints, if they fall into accessible frequency ranges, could be measured by pulsar timing arrays or future spaceborne interferometers. Detecting a spectrum inconsistent with a simple inflationary template would be a seismic clue. A second channel is in the distribution of primordial relics, primordial black holes, exotic particle species, or unusual isotopic abundances seeded in early dust. If certain energetic events preferentially produce compact objects or alter nuclear pathways, the downstream fossils could be detectable in the form of anomalous mass functions, unusual decay products in meteoritic samples, or isotopic ratios that fail to match stellar nucleosynthesis. These traces would be local and particulate rather than global, small anomalies in the geological or meteoritic record rather than a cosmic billboard. Third is the subtle route through biology and cognition. Human minds evolved in environments shaped by cycles of seasons, floods, droughts, and migrations. Those environmental rhythms produce cognitive templates, pattern recognition circuits predisposed to certain narratives. But evolutionary constraint alone does not immediately explain some cross-cultural motif-specific forms. For instance, the ubiquity of deluge stories with precise narrative elements across societies with no contact. Here, a cautious path forward is comparative. Catalogue the motifs, measure their formal structure, and test whether the distribution of patterns exceeds what convergent cognitive ecology would predict. If a statistical excess persists, especially if correlated with physical anomalies, a spike in archived isotope ratios at the same stratigraphic depth across disparate locales, for example, then the correlation would be worth investigating. This is where mythology and religion become evidentiary allies rather than mere comfort. Myths are not eyewitness accounts, they are compressed compilations of experience, memory, and symbolic processing. They are robust against superficial change and can persist for millennia, evolving yet preserving structural cores. If a fragment of cosmological memory leaked into human experience, it would be translated, transmuted, and ritualized. The resulting motifs would be shaped by cognitive affordances, narrative simplicity, mnemonic patterns, ritual utility, but the presence of a trans-cultural motif with structural complexity that resists simple ecological explanation becomes a signal, rather than noise. The appropriate response is not to claim the myth is literal history, but to treat it as a hypothesis generator, a lead that directs where to dig, which strata to sample, which ancient sediments to measure at high precision. There is both romance and method in that approach, Imagine, for example, a network of flood myths that share a constellation of specific features, trapped island worlds, skies opening, animals as witnesses, a rebuilt order with a particular divine calculus whose distribution does not track known contact networks and whose commonness is disproportionate to what environmental convergences predict. A responsible scientist would not assert that this proves a cosmic leak. What they would do is overlay the cultural map with geological and isotopic maps. Are there synchronous signals in marine transgression markers, in manganese nodules, in meteoritic spheral layers? Are there transuranic anomalies in lunar regolith dated to epochs corresponding to hypothesized cycles? Does the timing cohere with any cosmological signature found in the CMB or in the low-frequency gravitational background? Each cross-check is a statistical test. Each negative result narrows possibilities, and each positive anomaly elevates an otherwise idle myth into a vector for scientific inquiry. The program naturally broadens. Neuroscience can contribute by examining whether certain experiential phenomena, déjà vu, collective trance, or archetypal dreams have measurable correlates that track environmental triggers common across human habitats. Paleogenetics can test whether population bottlenecks or sudden migrations correspond with anomalous deposits. Geochemistry can probe improbable isotope ratios in the oldest zircons and in shield rocks that are least affected by later recycling. Planetary science can interrogate the Moon and Mars for isotopic or elemental oddities that resist simple meteoritic or solar wind explanations. Cosmology can refine models to predict the kinds of imprints a given pre-hot event would leave on the gravitational wave spectrum, and on the statistics of low multipoles in the CMB. These are not isolated curiosities. They are an integrative research agenda that treats myth and matter as different strata of the same investigative quarry. The idea that cultural memory might access cosmological memory invites a second, deeper reflection: the role of intuition. Human intuition is an evolved faculty for pattern detection. It excels at stitching sparse cues into coherent narratives. In environments shaped by cycles, intuition becomes the engine of survival and storytelling. It is plausible that long-accumulated cultural heuristics, ritual, taboo, mythic tabulation, encode effective strategies for coping with rare but catastrophic events. In that sense, mythic echoes are not miraculous transmissions from another universe, but efficient cultural codings of low-frequency disasters. Distinguishing between these explanations is subtle. Both produce similar surface phenomena. The discriminant lies in correlation with a physical signal that is otherwise unlikely, a gravitational background with a shape. Inconsistent with known mechanisms, a concentration of exotic isotopes in the oldest accessible minerals, or a distribution of primordial compact objects whose mass spectrum is best explained by non-standard seeding. At stake in this inquiry is not merely the seduction of cosmic romance. There are practical consequences for how humanity preserves knowledge. If cycles can, in principle, collate entropy into inaccessible degrees of freedom or leak information into adjacent domains, the lessons about redundancy and modality of storage gain new urgency. Cultural persistence strategies, encoded in rock, orbit, and field, must be designed with multiple failure modes in mind: geological recycling, cosmic scattering, and cosmological horizons. That means distributed archives, isotopic messages locked in refractory minerals, inscriptions on airless bodies that avoid plate, tectonics, gravitationally encoded signals if such engineering were ever feasible, and robust oral and ritual traditions that preserve structural knowledge without reliance on fragile media. Whether or not residues from previous aeons actually found their way into human myth, the logic of deep time preservation is indifferent to the answer. The longer the timeline one cares about, the more diverse and redundant the methods must be. This line of thinking also reframes the ethical and philosophical dimensions of memory. If human myths potentially contain echoes of cosmological history, then cultural heritage becomes not only an instrument of social cohesion, but also a rare archive of information that might matter to science. Reverence for ritual and story acquires a new kind of prudence. Treat old stories as compressed data with the potential to point toward physical anomalies, but also treat them with methodological skepticism. The task is to build bridges, not to assert metaphysical claims prematurely, but to let mythology inform where the probes go, and to let the probes, in turn, inform interpretation of myths. There are signs that this integrative work is already possible. Instrument sensitivity for low-frequency gravitational waves is improving. Pulsar timing arrays and proposed space interferometers promise access to regimes where pre-hot tensor modes could lurk. Geochemical techniques now measure isotopic abundances in single mineral grains with part per million precision, and sample return missions target pristine materials, less altered by Earth's restless geology. Comparative mythology has matured into a quantitative discipline capable of testing structural homologies against null models. Machine learning and network analysis can identify motifs shared by societies with minimal contact, and those selected motifs can be correlated spatially and temporally with geophysical datasets. None of this guarantees a discovery, but the convergence of tools across domains, cosmology, geochemistry, anthropology, and information science, makes the question empirically tractable in ways that, a generation ago, would have been purely speculative. The cultural impact of such a discovery, if it were to occur, would be profound. To find an imprint of a prior cosmological phase embedded in gravitational waves or in an isotopic oddity would rewrite origin, narratives across disciplines. To find correlated motifs in mythology that align statistically with physical traces would force a reassessment of how humans inherit knowledge. The intellectual response should be prepared, a careful, slow, methodical communal examination that recognizes the disproportionate psychological weight of such claims. The history of science is littered with premature narrativizing of slender anomalies. The right posture is therefore one of patient confirmation, multiple instruments, independent lines of evidence, and a willingness to accept no results as meaningful constraints. In the meantime, there is a quieter but no less important lesson. Listening to the oldest stories is itself a discipline of attention. That listening cultivates a cultural humility that is valuable regardless of whether cosmological residues are ever confirmed. Myths that speak of cycles, of floods, of mirror worlds, and of return gestures echo human attempts to find continuity in an indifferent universe. They are recipes for resilience, for making sense of discontinuity and loss. Whether those stories arose from cognitive convergence, from environmental regularity, or, more provocatively, from faint leaks of cosmic memory, they continue to serve a function. They keep communities oriented across time. The speculative program outlined here is intentionally conservative about conclusions and expansive about methods. It does not insist that parallel universes wrote notes into human myth, nor does it dismiss the possibility. Instead, it invites cross-disciplinary curiosity. Refine cosmological predictions about durable imprints, map gravitational wave spectra with patience, sample the geologic record. Where survival probabilities are highest, quantify mythic motifs with rigorous clustering algorithms and, above all, let surprising correlations prompt careful follow-up rather than ecstatic proclamation. At the end of this chapter, the listener should carry two impressions. First, that the physics of memory is a real and subtle business. Topology, tensor modes, and conserved degrees of freedom matter. And second, that human culture is itself a form of archive, extraordinarily good at compressing and preserving structural knowledge. If each cosmic loop leaves residues in adjacent realizations, the traces will be faint, statistical, and often ambiguous. Finding them will require patience, interdisciplinary humility, and instruments that listen across modalities, telescopes that read the sky, spectrometers that read stone, and analytical frameworks that read story. The project is not the triumphalist retrieval of lost civilizations, but a disciplined attempt to understand whether the cosmos has left hints of its own repetitions encoded not only in energy and matter, but in the patterns and rituals of creatures who happen, for a brief moment, to look up and ask, what if the most urgent question for a species was not whether it would survive the next century or the next millennium, but whether anything that could meaningfully be called it could ever survive the sweep of cosmic repetition? That question lands like a bell in the mind if the universe itself repeats, if eons fold into eons, or bounces into bounces. What happens to the fragile local embroidery of culture, knowledge, and selfhood that congregates briefly on a planet called Earth? Is humanity destined to be a pattern that reappears like a motif in an endless symphony, a faithful copy obeying cosmic script? Or is each instantiation irrevocably new, a variant that can nudge its future echoes by deliberate intervention? The thought provokes two immediate human responses that sit side by side, dread and a peculiar kind of hope. Dread, because the mechanisms that could erase memory are not metaphors but harsh physical processes: entropy rising, plate tectonics scouring rock, cosmic expansion erasing distant beacons, and, in the worst cases, violent cosmological finales that shred matter down to indistinguishable constituents. Hope, because even within those constraints, there are channels through which information is surprisingly robust, topological imprints, long-lived isotopic anomalies, gravitational wave backgrounds, and durable materials on airless bodies that accumulate evidence with geological slowness. The balance between the two determines the practical strategies and the moral calculus of a species that contemplates deep time. First, the question of repetition. If the universe repeats identically, determinism would appear to be vindicated at a cosmic level. Every decision, every thought, every life would reoccur, not as memory, but as reenactment, like a recording loop played again and again. But science offers reasons to doubt literal perfect repetition, quantum indeterminacy, chaotic amplification of minute differences, the statistical nature of thermodynamic processes, and the plausible influence of stochastic events in cosmological dynamics all point toward variation. Even in a cosmology that cycles, entropy considerations and quantum effects make exact recurrence physically suspect. The copy, if it existed, is more likely to be a close cousin than a perfect twin, similar broad strokes, different details, recognizable themes without identical sentences. That observation reframes the ethical and practical question. If exact continuity of individual minds is impossible, what should be preserved? The impulse to secure personal survival gives way to a more communal, cultural aim to preserve structures of knowledge, patterns of thought, technologies, and moral commitments that could catalyze flourishing in any future instantiation. In other words, if people cannot be copied across cycles, perhaps ideas can be. The task then becomes identify robust carriers of information, design encodings that survive geological and cosmological processes, and distribute them so that at least some fraction remain legible to any future intelligence that might arise. This immediately suggests a taxonomy of preservation media, each evaluated by its vulnerability to different erasures. Geological repositories, stable continental cratons, deep boreholes below the zone of plate recycling, and ancient shield areas are good at resisting surface weathering and erosion, but still subject to metamorphism and subduction on 100-million-year scales. Airless bodies, lunar regolith, certain asteroids, and the icy moons of the outer system offer far better stasis. They do not host plate tectonics. They do not rain. Their surfaces, while pelted by micrometeorites and modified by solar wind, preserve accumulations of material over billions of years. Deep space artifacts placed in orbits that resist decay or repositories tucked into stable Lagrange points can avoid planetary recycling but face slow collisional hazards and cosmic radiation damage. Beyond location, material choice matters. Refractory minerals such as zircons encase isotopic information that can survive geologic upheavals. Diamond lattices resist chemical alteration and can, in principle, host atomic-scale encodings, certain long-lived radionuclides and transuranics, if synthetically produced and embedded in resistant matrices, would constitute unmistakable anomalies to any future geochemist. The idea is not fanciful. An engineered excess of a particular isotope within a natural ratio could announce its provenance. Because known astrophysical nucleosynthesis produces specific, predictable patterns. An out-of-equilibrium abundance is a clear sign of intentionality, but producing such isotopic markers raises practical and ethical questions. The energy cost and technological sophistication required to manufacture telltale isotopes at scale are enormous, and the choice of what to encode and who decides carries moral weight. There is an information hazard problem. Certain knowledge, if recovered in the wrong epoch without accompanying safeguards, could be dangerous. Humanity's reflex toward grand self-documentation must be tempered by restraint. This is not merely sentimental conservatism. It is a sober assessment of responsibility when future intelligences, perhaps lacking the cultural maturity of their progenitors, stumble upon fragments of potent technologies. If cycles allow for the persistence of certain global modes, then signals encoded in cosmological fields are attractive in theory. Low-frequency gravitational waves, tensor imprints crossing eons, and persistent topological features of fields are less susceptible to local decoherence in galactic foregrounds. In practice, however, these channels are extraordinarily difficult to engineer. Deliberately shaping gravitational wave backgrounds requires manipulating macroscopic masses on scales and energies well beyond current human capability, even if the physics permitted. The resource and time requirements indicate that such interventions would be on the order of civilizations hundreds or thousands of times more advanced than ours. The practical upshot is that terrestrial strategies are currently limited to durable material, encodings, and to maximizing the legibility of records across a range of plausible future scientific repertoires. There is another sobering channel of erasure that comes from cosmology itself: cosmic acceleration. An accelerating universe carves event horizons, isolating regions of space and red-shifting radiation into oblivion. Over cosmological timescales, the sky that present observers red will darken, and the distant scaffolding of galaxies will slip from view. For the archivist thinking in eons, this is a constraint. The universe will forget grand-scale messages placed at intergalactic distances if dark energy behaves as a cosmological constant. The urgency this introduces is paradoxical and humanizing. If the present epoch is uniquely information-rich, then the moral imperative is to gather and protect knowledge now, while the cosmos still presents its full archive. Philosophically, the prospect of partial recurrence provokes reflection on identity and agency. Continuity of the species is one thing, continuity of the person is another. If future instantiations of human-like minds arise, they may carry variants of our moral intuitions, our cognitive biases, and our scientific insights. They may also reinterpret and repurpose legacy material in unpredictable ways. That is not failure, it is the nature of cultural evolution. The goal, then, is to seed adaptive patterns, ways of thinking, experimental methods, and ethical frameworks that are portable across vastly different material and historical conditions. Short, compact algorithms for scientific inquiry, compressed representations of mathematics and logic, and principle-based frameworks, for example, how to rebuild calorimetry, how to interpret isotopic anomalies, how to generate stable chemical syntheses, could be more valuable than encyclopedic data dumps that presume continuity of manufacturing capabilities. A further strand of hope emerges from humility, the human capacity for reflective self-direction. If the cosmos is not a deterministic loop, then choices matter not only within a single life, but across potential echoes. Small differences can amplify. A deliberate decision to seed the moon with robust isotopic markers, to dispatch durable information carrying artifacts to multiple airless bodies, or to store data across distributed geological and orbital vaults increases the probability that future intelligences will encounter vestiges of present civilizations. The moral upshot is unsettlingly simple. While humans cannot guarantee personal immortality, they can intentionally bias the distribution of future knowledge. The act of preservation becomes a long-range cooperative ethic, an expression of stewardship over possibility. That stewardship raises institutional challenges. Preservation across geological and cosmological scales must outlast political cycles and cultural fashions. It demands governance frameworks that think in centuries and millennia, not election cycles. It implies funding and infrastructural commitments of a different order. Missions to return pristine samples from lunar far side and from certain asteroids, construction of subterranean vaults in Quatons, repositories of hardened data in multiple languages and encoding schemes, protocols for what to encode, prioritizing universalizable knowledge, mathematics, basic chemistry, and durable markers of provenance over contingent technologies that could be misused. Building such durable architectures is a social task as much as a technical one. It requires international collaboration, shared commitments, and norms around openness, redundancy, and responsibility. There is also a moral complexity intrinsic to the hope of influencing future copies, the danger of hubris. Choosing what to preserve is choosing a narrative about value. Whose art, whose science, whose ethics will be encoded? The impulse to cement the culture's triumphs into stone, literal or figurative, can reproduce biases and impose a version of history on beings who did not consent. The ethical approach demands pluralism, redundant encodings in multiple cultural modes, multiple languages and multiple formats, and a humility that recognizes preservation efforts are gestures, not guarantees. Technically, a sensible portfolio balances local and cosmic strategies. Locally, embed isotopic anomalies in lunar regolith, and in deep, shielded mineral matrices on Earth create durable physical messages encoded in diamond or refractory ceramics, scatter redundant catches on multiple airless bodies to hedge against catastrophic planetary turnover. Cosmically, pursue gravitational wave astronomy to test whether any pre-aeon imprints exist. Refine models linking cosmological dynamics to potential survivable channels of information, and map the near-term sky while the observational window remains open. Crucially, invest in sample return and in the careful archiving of Earth's best-preserved ancient materials. The oldest zircons, continental shield cores, and meteoritic collections so that any unexpected anomalies can be correlated across data types. Hope also resides in intellectual resilience. Regardless of whether copies recur, the act of trying to be heard across deep time enriches present thought. It clarifies priorities, forces cross-disciplinary rigor, and cultivates humility about the fragility of evidence. The search for pre-Aeon imprints has catalyzed improvements in precision instrumentation, statistical methodology, and the social architecture of large-scale science. Those improvements yield practical benefits here and now: better climate reconstruction, improved understanding of planetary evolution, and a more mature epistemic culture, less prone to premature, sensational claims. In that sense, the quest to be legible to the far future refines how humanity understands its immediate past. Finally, there is an existential lesson woven through both risk and hope. The recognition of scale itself reshapes meaning. The tiny, bright episode of life on Earth is precious precisely because it is ephemeral. Whether the cosmos repeats or not, the moral project remains to make the present count. To do so is not simply to preserve data. It is to cultivate virtues, curiosity, restraint, openness to correction, and generosity toward possible successors. The desire to leave a trace is not narcissistic if it is paired with prudence and respect for unknown others. It is a form of solidarity extended across time. In the narrow sense, humanity cannot assume personal continuity across cycles. Physics suggests identity is not an object transferable through a cosmological reset. In the broader sense, however, humanity can aim for continuity of knowledge, method, and moral imagination. That aim is both practical and symbolic. Practical, because certain encodings and repositories can materially increase the odds that later intelligences will reconstruct essential scientific knowledge. Symbolic, because the project asserts that transient beings can act responsibly toward the deep future. As the inquiry closes, two imperatives emerge. First, act now with humility and rigor. Build distributed, redundant, ethically informed archives, expand cosmological observation while the window is open, and develop the interdisciplinary methods that can interpret faint, ambiguous traces. Second, cultivate a cultural disposition that values patient custodianship over spectacle. The universe may repeat, or it may not. Either way, the act of preparing for the possibility of making careful choices about what to leave and how deepens the moral and intellectual life of those who undertake it. If the cosmos is a palimpsest, then humanity's task is not to demand permanence, but to add resilient, intelligible strokes to a page that might one day be read by minds as eager and as fragile as its authors were. The smallest prudent gestures now, an isotope here, a vault there, a constellation of observations recorded with surgical care, are the most durable form of hope. What is the most provocative answer to the question of beginnings and ends is that there are none, only a circle that keeps turning. The idea that existence might be organized not as a line with a single point of origin and a single terminus, but as a ring of passages, invites a particular kind of reverie. It shifts the problem from the origin of everything to the persistence of pattern, what it would mean for the cosmos to be, in some sense, indestructible, and what that indestructibility would owe to the physics of space-time, to the bookkeeping of entropy, and to the stubborn appetite of curiosity that lives on one small world. The endless loop is not a trivial or poetic flip of perspective. It is a scientific hypothesis with multiple faces, bounces that reverse contraction into expansion, conformal rescalings that reframe an eon's cold end as the hot beginning of another, collisions of higher dimensional brains that ignite new thermal histories, each idea carrying its own set of consequences for observability, for the survivability of information, and for the ethical horizon of a species that contemplates a future measured in eons. What binds these scenarios together is a shared moral. Continuity may be possible without sameness. Eternity may be a tapestry of variations rather than perfect repetition. That distinction holds practical implications for the search for traces, for preservation strategies, and for how humanity frames its own place in time. The first practical consequence of a cosmic loop is a reassessment of what can survive. Not everything that exists is equally durable. Thermal baths and violent compression scramble microstates. Inflation, if present, can stretch pre-existing irregularities beyond causal contact. Accelerating expansion can consign information to horizons from which light will never return. Some carriers of structure, however, are more resilient. Topological features, Knots in fields, defects in the arrangement of space, are, by their nature, not easily erased by local processes. Gravitational waves travel with a dignity that photons sometimes lack. They pierce plasmas and cross epochs with far less scattering. Conserved quantities, global charges, and long-wavelength tensor modes are, in principle, candidates for cross-aeon persistence. From this realization flows a corollary. The search for cosmic memory must be strategically conservative. It cannot expect literal artifacts, machines, inscriptions, intact devices to survive the scale of processes that remake planets and perhaps entire universes. Instead, it must prioritize the subtle and the statistical. It must tune instruments to the quietest channels, the low-frequency hum of a primordial gravitational background, particular non-Gaussian features in the cosmic microwave background with shapes that do not fit simple inflationary templates, the anomalous mass functions of compact objects, or the peculiar isotopic anomalies locked in the sturdiest mineral grains. The work is not glamorous. It is incremental, technical, and exacting. But if a whisper of a prior aeon exists, these are the frequencies at which the whisper is most likely to be heard. This methodological conservatism is also emotionally resonant. There is humility in the acceptance that large, obvious traces are unlikely. There is, simultaneously, an exhilaration in knowing that tiny signals can convey grand histories. A universe that cycles leaves no guarantee of readable messages, but it does not preclude them either. The difference between impossible and improbable is often a matter of instrument sensitivity and of patience. For scientists, the loop hypothesis becomes a long-term research program. Build better gravitational wave detectors, press CMB maps toward ever lower noise floors, sharpen pulsar timing arrays, and develop geochemical assays capable of teasing apart isotope ratios at unprecedented precision. For the species that hosts that science, the loop hypothesis becomes a cultural imperative to sustain institutions of inquiry long enough and robustly enough that the quiet signatures of cosmic repetition, if they exist, are eventually resolved. There is, inevitably, a counterweight of doubt thermodynamics. The second law, that relentless, empirical account of entropy's increase, seems at first glance to banish the possibility of perfectly repeating cycles. If every aeon increases total entropy, how could a later aeon start with the low entropy conditions required to produce the kind of ordered complexity observed in our own thermal youth? Several proposals attempt to reconcile this tension. Some models suggest mechanisms by which entropy becomes sequestered, pushed behind horizons, or concentrated in structures that decouple from the degrees of freedom of the emergent aeon. Some rely on quantum gravitational effects at extreme densities to rewrite the ledger in ways we do not yet comprehend. Others invoke mathematical rescalings that change how entropy is measured across conformally related geometries. None of these answers is yet definitive. What matters is the admission that the question is scientific. It is about conserved quantities, boundary conditions, and the dynamical behavior of fields at energies that will remain stubbornly difficult to probe. The loop hypothesis, therefore, is not a metaphysical whim. It is a set of concrete constraints and predictions that can be tested, or at least bounded, with better instruments and more patient analysis. If the universe is indeed a series of aeons, each with its own thermodynamic life, then immortality shifts from the literal to the structural. The cosmos, as an entity, may lack mortality in the sense of a single, definitive annihilation. Its cycles may continue in ways that make the fabric of existence persist. But that persistence does not extend straightforwardly to particular arrangements. No single planet, civilization, or mind is guaranteed to cross cycles intact. Immortality becomes the persistence of possibility, the capacity for ordered complexity to arise again somewhere in the network of instantiations. That is a different, subtler kind of continuity. It is not the survival of singular things, but the endurance of the conditions that allow things like memory, curiosity, and life to re-emerge. Human curiosity, then, earns its own quiet immortality. Curiosity is not a single mind or a single artifact. It is an activity, a pattern of inquiry, of observation, of interpretation that can be instantiated repeatedly when the conditions permit. If the cosmos cycles and the physics that govern the emergence of complexity remain similar across eons, then the likely recurrence is not of particular individuals, but of the very capacity to ask questions about origins and ends. In that sense, curiosity is a habit that the universe can foster multiple times. It is a cultural gene of sorts, replicable wherever matter organizes in ways that support information processing and self-reflection. The endurance of curiosity is not guaranteed, but it is plausible in a cosmos that repeatedly creates hospitable niches. These reflections yield actionable priorities. The first is observational. Invest in the instruments that can read the faintest archives. Expand international collaborations for pulsar timing arrays to map the nanohertz gravitational wave background. Support spaceborne interferometers capable of reaching picohertz bands. Keep pushing CMB experiments not only for sensitivity but for better control of foregrounds and instrumental systematics. In planetary science, prioritize returns of the most pristine, least altered samples. Ancient zircons from continental shields, deep regolith from the lunar far side, icy cores from outer system moons, and well-preserved meteorites. Treat these samples as not merely geochronological resources, but as possible repositories of anomalous signatures that deserve cross-disciplinary scrutiny. The second priority is preservation, informed by realism. If human intentions aim for durability, then redundancy and modality are essential. Redundancy across locations hedges against local catastrophe. Place repositories in multiple stable cratons on the Moon, on certain asteroids, and, if feasible, at Lagrange points where orbital stability supports longevity. Modality matters because different media age differently. Isotopic anomalies locked within refractory minerals. Messages inscribed in diamond matrices at atomic scales. Encoded knowledge stored in diverse languages and formats. Analog backups of vital mathematical structures and metadata that teaches future discoverers how to decode the messages. These strategies are not merely technical choices. They reflect an ethic of stewardship that engages successive generations in a shared project of long-duration care. The third priority is cultural. Cultivate the norms and institutions that can carry long-term projects across political and social cycles. Preserving knowledge for deep time is not a one-off engineering problem. It is a governance challenge. It asks for frameworks that prioritize continuity over short-term gain and that encode responsibility into the architecture of funding, education, and international cooperation. This is an ethical design problem as much as a technical one. Who decides what to preserve, how to balance risks of misuse, and how to ensure inclusivity so that the record is not a narrow imprint of a single culture's vanity. All of this work building detectors, archiving intentionally, and teaching future curators serves a philosophical orientation that deserves explicit naming. It is a posture of patient humility. Recognizing the fragility of evidence and the possibility of cosmic recurrence should not breed nihilism. Instead, it can cultivate a sober creativity, a commitment to design for resilience, to value redundancy, to invest in instruments that can hear the faintest echoes, and to build cultures capable of long-range thinking. Humility here is active. It is a discipline for how to act in the face of timescales that dwarf lifetimes and institutions. There is a final human dimension that ties the cosmic loop back to everyday meaning. An endless circle reframes legacy not as individual immortality, but as contribution to a longer causal thread. People cannot assume that their names or faces will be legible 100 million years from now. They can, however, contribute to the endurance of ideas, methods, principles, discoveries that increase the likelihood that curiosity will reemerge and flourish in future instantiations. The ethic that emerges from this understanding is not resignation. It is an oriented form of generosity. Invest in the conditions that allow future minds, not copies of present minds, but new minds, to ask and to answer the questions that mattered to their predecessors. In the end, the circle is both a constraint and a consolation. It constrains by reminding that not all marks are equally durable and that entropy, expansion, and violent transition are real and unforgiving processes. It consoles by showing that persistence does not require the survival of particulars, structural features, conserved patterns, and the disposition to inquire can reappear whenever physical conditions permit. The universe may be an endless score with repeated themes, sometimes varied, sometimes fractured, but always permitting the possibility of new arrangements that can, again and again, cultivate the habit of asking. So the practical human response becomes twofold: to persist in the patient work of detection, listening where the cosmos keeps its quietest records, and to act as conscientious stewards of knowledge, building multiple, diverse strategies to preserve what matters. The first task buys the chance of discovery, to find, in the faint curls of background radiation or in a whisper of gravitational waves, an echo that tells of an aeon before this one. The second buys the chance of influence, to increase the odds that whatever of human experience deserves to outlast the present. Epoch will survive sufficiently intact to be useful to minds that may not yet exist. The metaphor most fitting for the conclusion is not a closed loop that traps its inhabitants, but a ring that allows passage, a circular highway where cars do not necessarily return to identical positions, but where the road itself remains. The cosmos, in this image, is less a prison of repetition than a stage for repeated creativity. To be part of that stage is not to claim immortality, but to play a role in the continuity of possibility. It is a modest, dignified ambition, to leave traces that are intelligible, to listen for traces that may already be present, and to cultivate the institutions of curiosity so that, whatever the universe's deep temporality, the human urge to understand can continue to work its small, persistent magic across the vast rhythm of time.